In the past year, I've helped thousands of people land their dream offer in AI engineering. I myself recently landed offers from companies like Amazon and Google, paying over $200,000 a year. And the number one factor that has helped me and all of my students land incredible job offers is our portfolio. So in this video, I'm going to walk you through a very special portfolio project, implementing a transformer from scratch, line by line. We're going to build the model that powers ChatGPT, Claude, Gemini, and every major LLM today. In the first half of the video, we'll go over the key concepts, and in the second half of the video, we'll write the code. And make sure you get through at least the first half of the video, because without understanding the concepts, the code isn't going to make sense.
Okay, let's solve a GPT dataset. Before we start building the actual GPT class and talking about how we can actually generate text from transformers, we should do one problem where we prep the dataset that's actually used to train GPTs. So you may have heard that ChatGPT was trained on the entire internet, where the entire internet can be thought of as some body of text. So in this problem, we're actually going to break down what that means in the code. So we can actually take some sort of giant body of text, and from this body of text, we create examples for the model to keep learning to predict the next token based on different contexts. So these chatbots, these large language models, the way they work is they keep predicting the next token, which might be like the next character or the next word or even the next subword. They keep doing this over and over again until they have some sort of big paragraph that they've given back to you. But the way they even learn to do this, what they're really good at is predicting the next token in a sequence. Given like some words or some incomplete sequence, it can complete it. It's like autocomplete on steroids. But the way they actually do that is what we're going to learn in this problem, or rather the data set that actually helps them do that. And we're going to write a function called batch loader, which is going to set up a batch of training examples. And that tensor needs to be of size batch size by context length. And we also need to have the appropriate labels for this data set so that then during training, we can calculate the loss or the error between the model's prediction and the correct labels or the true answers. And we will explain what context length and batch size are soon. And there's just an implementation tip on what function we're supposed to use. So we're given some sort of string, which is just the raw data set. That's before we're going to do any processing on this, actually creating the examples. We're also given something called context length. And this is actually how many tokens back can the model factor into its response back to you. So how far back is it actually taking into account? How many tokens back can it quote unquote read? And this is also going to be the length of each training example. It's going to be of length capital T, which represents the context size. Each training example that we create, which will be like, say, a substring from this giant body of text, this giant string, each of those is just going to be of length capital T. And then how many sequences or independent examples do we want to generate? That's just the batch size. And we just need to return X and Y. So let's look at an example now. So the way we actually get our data points X is we pick batch size, or I'll just refer to that as capital B. We'll pick this many random different starting indices for our substrings of length capital T. And all those substrings are just like valid starting indices. All those starting indices just need to be valid starting indices inside our raw data set. And when I say valid starting indices, they need to be far left enough in the data set such that you can actually extend capital T tokens to the right. So we're going to develop those starting indices first, and that's going to then explain our example over here. So we have hello darkness, my old friend as a string, capital T equals 3, batch size equals 2. So let's say the first random index we choose is 1. So that corresponds to darkness being the starting token. And with a context length of 3, we would say darkness, my old. So that ends up being our first example in X. And then the way Y works is Y contains the tokens that the model is supposed to actually predict, the right answers that the model is supposed to predict. So when we have a sequence, it turns out there's a bunch of training examples within them. If we have darkness, my old, Well, the model can learn predict what comes next given a context of darkness. And we know my comes next. The model can also learn that if you have darkness my, then old comes next. And the model also needs to learn, given this entire sequence, that darkness my old, that friend should come next. And that's exactly what you'll find in the corresponding index for y. The first label, or the first right token that the model needs to learn to predict is my. That's just given darkness. Given darkness my, we need to predict old. And given darkness my old, we need to predict friend. The second random index that's chosen is actually index 0. So that would be hello as our starting token. And if you follow that same reasoning, then this example should also make sense. So our goal here is actually just to prep this data set and specifically return these two tensors, x and y, and both of them are essentially containing strings. And it's highly recommended that you solve the NLP intro problem before this one, because that one actually explains that before feeding this into the model for training, you would actually encode each word as an integer. You wouldn't directly pass in strings into the model, but in this problem, it's okay to just return strings. So in the code, we're going to start off by actually splitting up our raw data set into words, since we know we're going to be taking essentially substrings or sublists to actually return or get the words in our output tensors. So the main thing we need to explain is how to actually use torch.randint. So the lowest index is going to be 0. For size, we can actually pass in a tuple, where this tuple is just of shape batch size by 1, since we essentially just want a vector or a tensor of length b, since we want b different random numbers. And we need to figure out what high should be. So this upper bound is actually exclusive. It will not include it will not include the number for high. That won't be a valid random number. So that's kind of the case for a lot of Python functions. And what we actually want to use is just the number of words minus capital T. So imagine capital T is 1, then this is number of words minus 1, essentially the final index. But if this is exclusive of that, then we would not include the final index as a valid starting index, because we want to still have capital T. We want to still have capital T remaining tokens left after the starting index so that we can actually have the complete Y, right? Y contains our labeled answers. So if the starting index was like one of the last index in our list of words, then that wouldn't actually make sense because there's no word after that for the model to actually learn to predict. So once we have our list of words, it's just going to come down to actually taking the right sublists. So whatever our starting index is, and of course this is different for x versus y. Y would have a starting index that is 1 greater since we start predicting the next token. We just need to go all the way to start index plus t. So let's jump into the code. So let's start off by generating our random indices like the starter code tells us to. So we can say something like indices. We're going to use torch.randint. We can say that indices is torch.randint, and we just want to set low equal to 0. We want to set high equal to however many words we have, right? So maybe we're going to do some sort of split and call that the words minus the context length, right? And then we know the size can simply be a tuple, which is just, of size batch size. So that's indices, but we need to know how many words we have. We need to actually get that list of words. So we can say words is raw dataset dot split. By default, we're going to split on the space delimiter, which is going to break that string up into a list of words. And now we can actually get x and y. So we can say x is going to be some sort of list. Then we can say y is going to be some sort of list. And then we can go ahead and say for each index in indices, we can generate each of our batch size different examples, right? The length of x will be batch size and the length of y will be batch size. So x.pend, we can actually just take a sublist of words from index to index plus context length. And that's it for that entry in x. And then similarly in y, we're trying to start predicting the next token, right? So we'd say index plus 1 all the way to index plus 1 plus, again, context length. And that's it. We simply return a tuple of x and y, and we're done. And we can see that it works. So this problem teaches us that training a transformer, training a language model, is just about generating a data set where the model can keep learning to predict the next token in the sequence. So now that we know what the inputs and outputs are, now let's actually start jumping into the neural network architecture for transformers. The next problem is on self-attention, a very complicated problem at first, although we'll definitely break it down and make it fairly intuitive, but it's definitely the crux of how transformers work. Okay, let's explain attention, and specifically self-attention. So here we have a really complicated looking diagram, which you may have seen before, and it's called the transformer architecture. It's essentially a neural network architecture that was used for ChatGPT. Specifically, we don't worry about the left part, which is called the encoder, and we only use the right part of this architecture, which is called the decoder. And here we can see the different layers in this neural network. We can see that embeddings are used in this neural network. That's a really big part of ChatGPT. Then we also have linear layers. Obviously, those traditional feed-forward neural networks. There's also another one over here. Just the distinction between this linear layer and the feed-forward is that the feed-forward includes like linearities like ReLU and sigmoid, right? But actually, one of the most important parts of this architecture, the part that makes ChatGPT and modern-day chatbots so effective, way more effective than previous chatbots in previous years, is the concept of attention. And attention is one of the most important topics in NLP right now. So let's go ahead and explain exactly how it works. So what is the point of attention? Let's say we're working with some chatbot and we pass in something like write me a poem. This is a kind of a complicated instruction for a computer to parse, but we know that ChatGPT can actually respond really well to this. Well, the input will be something like B by T, right? And let's just say we're passing in only one sentence or one example right now. So B is 1. And T will be the number of tokens. If we're breaking things up on a word level, then T equals 4 here. The first step would actually be the embedding layer, right? This was actually the first step in, say, our sentiment analysis model. And as you may have seen in the transformer diagram previously, the first step is the embedding layer. So for every token, right, for every word, every time step, however you want to think about it, we are going to generate the embedding vector. And that will be of size C or embedding dim. Those might be kind of the symbols used for that. So this is what I've kind of represented over here. If B is 1, right, then we don't have to worry about B by T by C. Let's just say it's T by C, right? Then in the first row, we have the embedding for the token, right, and that's some vector. In the second row, we have the embedding for the token me, and that's some vector, right? But how does the model actually combine or aggregate all this information to get a sense of what the instruction or the task is, right? How does the model understand the relationships between tokens? Because there's actually many pairs of relationships that are important within this task or this command that the chatbot is given. For example, what is the model supposed to write? It's supposed to write a poem, not a movie or a book. It's supposed to write a poem, right? There's many pairs of relationships between tokens that the model needs to take into account, and the model somehow needs to aggregate or combine all these embeddings together. Because right now these are all separate independent rows, right? Each row in this tensor is a time step, right? But we need to somehow aggregate and combine them together. Well, the simplest way to do that is just by averaging, right? Let's say we have a sequence of tokens, right? So we have write as at the 0th time step, and then me, and then A, and then poem. And write is the first token. So let's say it doesn't get averaged with anything. But then me is the second token. So to get a more complex representation that actually factors in the sequential nature of this sentence, or at least the spatial relationships that are going on, let's say we average me and write together. So it's kind of like a running average. And then we have A. So then A would get averaged with write, me, and A. And then finally poem. Well, poem would actually be averaged with itself and everything that came before it. So it's essentially going to be represented. The representation for poem could then be the representation for the whole sentence averaged together. And this can work, and we can get decent results in neural networks with this, but not the greatest results. And this might remind you of what we did in the sentiment analysis problem, where we just averaged our embeddings together. We just did a simple average. It's a simple aggregation. But we actually want to develop more and more complex aggregations, right? So before we can do that, let's first start to think of this aggregation, this simple aggregation we did, as a matrix multiplication. So here we have our t by c, right? You can think of each row in this tensor as being the embedding for a token. And I'm just following like row column notation here. So this is row 1, column 1, right? Row 1, column 2. That's kind of the subscript notation there. And this simple running weighted average that we just talked about, you can think of it as a matrix multiplication. So imagine that we left multiply it. So on the left, we have this tensor that is t by t. So t is 4 in this case, right? If it's write me a poem, that's 4 tokens. So we have a t by t tensor that is going to multiply against the t by c tensor. And this is going to help us end up with a t by c tensor again. And in every row, what we're going to have, at least at the entries that are non-zero, is just 1 divided by the number of tokens. And then everything that comes after it is 0 for the first row. Everything that comes after the first 2 tokens is 0 for the second row, and so on. So, and once we actually do this matrix multiplication, remember we're doing this row times this column to get this number, right? And then similarly, we would do the first row times this column to get this number, right? And similarly, we would actually be doing this row times this column to get this number, right? Once we actually do that, let's see what we get. So initially, just for the first row, right, this would just be dealing with the first time step, first time token. It looks like it doesn't get averaged or added anything else into it. It just kind of gets scaled with a factor of 1/4 for both the entries in the 2 embedding dimensions we have. Then for the second time step, we can see that we essentially are taking 1/4 times what came before it, and also 1/4 with what we currently have. And we can see the same thing being done here. 1/4 of E1, 2, which is essentially what came before it, and then we add in 1/4 times E2, 2, which is exactly what was there. And this is essentially that running weighted average that we were talking about earlier. Because what is an average, right? You're adding everything up and you're dividing by the number of examples. But if your number of examples is essentially constant, you can kind of pull that out. And the 1/4, the 4 that you would be dividing by, if you were, say, adding everything up and then dividing by 4, that's kind of what a running average would be doing, right? We can essentially just distribute that 1/4 to each number that's being averaged, right? So just to make this super clear, here we have 1/4 times E11. Here we have 1/4 times E11 plus 1/4 times E21. So that's kind of averaging right and me. And then here we have 1/4 times E11 plus 1/4 times E21 plus 1/4 times E31. So this is kind of the average of write me a, right? As we get more words and more further along into the sentence, we get more and more context that gets taken into account. And this is being done for this column over here, and kind of the similar thing is being done in this column over here. Because remember, in this case, C equals 2, the embedding dimension is 2, but we are averaging along the time dimension. So this is essentially nothing more than what we already talked about over here, right? We talked about how we want some way for the model to know what's important to pay attention to and what the relationships are between each sentence. So for every token, we average itself with what came before it. Write gets averaged with everything with itself and what came before it, which is nothing. Me gets averaged itself with everything that came before it, which is just right, and so on, right? And that can actually be represented as a matrix multiplication, where we just take the t by c embeddings and we multiply on the left with this t by t tensor. But the fact that this tensor, which contains our weights for this weighted average or aggregation, the fact that it's t by t actually means something. So the fact that it's t by t means that for row I, column j, inside this tensor, we can interpret that as the strength or affinity or score, as you may hear, between token I and token j. So we can think of the first row of this t by t matrix as corresponding to the row for write, and then me, and then a, and then poem. And similarly for the columns, this is the column for write, me, a, poem. So if I were to look at this number right here, well, that's write, me, a, and then write me. So this 1/4 over here that I'm circling should actually be a number that symbolizes the strength or of the connection or the relationship between the words me and a in the input sentence. But that doesn't seem like a particularly important connection, right? What's probably more important is the connection between the tokens write and poem, right? Because what are we writing? A poem. The model needs to understand that there is a strong relationship between these two tokens. So ideally, we would actually want this number over here to be very high because this row is for poem and this column is for write. So we have this t by t tensor. We kind of interpret row I, column j as being the strength or connection between the token for row I and the token for column j. But we want to actually have a weighted average, right? This is just a simple average. Everything is just 1/4, but we want to have a weighted average. We want to have a weighted average so the model can actually pay attention to some tokens more than others. Because in a given sentence, write me a poem, the word a isn't really that important to pay attention to. Maybe it's somewhat related to the word poem because the model needs to output only one poem instead of multiple poems, as opposed to if we said write me poems. So the word a does have some significance in that command that we're giving into the chatbot, but it's not the most important to pay attention to. We don't want to weigh everything equally with this whole 1/4 or 1/t situation. Instead, what we want is we want a weighted average, right? But how does the model for any arbitrary command that it's given, any arbitrary sequence of tokens, how does it actually learn what the weights inside this t by t tensor should be? That's what the self-attention layer accomplishes, and there is a bit of a complex mathematical formula, but we'll break down exactly how that works. So just to make it super clear on what the whole point of this self-attention layer in a neural network is supposed to accomplish, is it's supposed to actually come up with weights. Specifically, it's supposed to come up with a t by t tensor of attention weights or attention scores, where we can figure out how important each token is to every other token. So I went ahead and crossed out the future tokens, right? So for high is right here in the first row. High shouldn't be able to look at any of the future tokens. We only want to look at the current token and what came before it to figure out what comes next, right? And I didn't exactly make this explicit earlier, but how these language models like chatbots work is continuously prediction of what's going to come next in the sequence. We'll talk more about that later, but let's focus on trying to understand this t by t tensor for now. One number that we can see that is particularly high is for the row corresponding to the question mark and the column corresponding to high. We can see that we have a number 73 there, which is relatively high. So why would that number be relatively high in the t by t tensor for this particular input? Well, the fact that how is associated with the question mark means that we're actually asking a question, right? The word how can be used in various contexts in English. We can say, that's how that works. That's just kind of declaring something. It's stating some kind of information. But if how is associated with the question mark, then the model can learn that the word how is being used to form a question here. So the goal is to actually have a layer in our neural network that, given our embeddings for every single token, we can then generate a t by t tensor that tells us for every pair of tokens how important they are to each other. And we actually want that to be like trainable and learnable through gradient descent based on our training data. And then we can use that t by t tensor, multiply it against the embeddings like we did previously, right? What we did is we took our t by t tensor and we matrix multiplied it against our t by c embeddings. That's what we want to do. And then our output can then be kind of sent on and forwarded through later parts of the neural network. So now let's try to understand how this t by t tensor is actually going to be generated. What's the formula for this layer? So there's kind of an ugly looking formula for self-attention if you just Google the formula for self-attention. Here's the formula to get the t by t scores, and then the layer output will be the scores times something called v, which is similar to the thing that we multiplied scores by previously. But the main things that we need to talk about here are what in the world is q, what in the world is k, and why are we raising it to the power of t and then multiplying them together, and what is v. dk is also something else that we're going to talk about, but it's very similar to the embedding dimension. And the softmax is also something that we'll talk about, but it's pretty straightforward. It's kind of like the sigmoid function in the sense that we can kind of squeeze our values to be between 0 and 1. Because if we go ahead and take a look at the previous picture that we were looking at, these values are not really constrained to any kind of range, right? We want to normalize them and set them to be in some kind of fixed range where the highest value is 1 and the lowest value is 0, but the scale and relation or the ratios are still kept. So that's what softmax does, but the main things we really need to explain are what is v, what is Q, and what is K, because those are the main things that make up self-attention. So let's break that down and make it really intuitive. So let's explain the Q in that formula. The Q in that formula actually stands for query. So in our attention model, we are going to have every single token in the sentence actually be able to quote unquote talk to the other tokens and communicate with each other until they pair up and we figure out the right T by T scores. And the way that we're going to do that is by having every token. I've only drawn it for write and poem right now, but every token is going to emit. It's going to emit and send out a vector called a query. And just like the word query means, this vector is going to contain information that represents what that token is searching for. What is its query? So maybe if we were using a character level language model and our token was like Q, then Q might be emitting some sort of vector of information that represents what it is searching for. And we know that in the English language, U almost always follows Q. So it might be that information in that vector that the token Q is emitting out. If we just had Q as a token using a character level model instead of a word level model, the vector that Q is emitting might contain information or numbers in here that are similar to what U has. So Q would then match up with U because U would be a vector that emits its own information. And what we're going to do is we're going to have every token emit this query vector, and that query vector is going to be of size attention dim, which will be a parameter specified to you. And that can kind of be then represented as a linear layer. That's how we're going to generate the queries for every single token. It's simply going to have embedding dim as the input number of features, because right now, before we even generate the queries, we know that for every token, we have a vector of size embedding dim. That's how we kind of have that represented. And then we're going to actually change the dimension to attention dim so that every token in this sequence is emitting a query of size attention dim. And that represents what the token is looking for. So if every token emits a query vector representing what it's looking for, every token also should emit a key vector representing the information that it has. And then we can kind of match up the queries with keys. The tokens can kind of pair up with the tokens that are actually relevant for themselves. And then the T by T scores are actually learned. So every token is also going to emit a key vector of size attention dim. Again, I've only drawn this for write and poem right now, but this will be emitted for every single token just as the queries were. And this will also be generated using a linear layer, which of course has, those trainable W's and biases. And then what we do is we take that query matrix, which is T by A, because for every token at every time step, we have a vector of size A, attention dim, specifically being the query. And then we're going to multiply that by K transpose. So we have that matrix over here. That one, instead of being T by A, because we've transposed it, it would be A by T. And that's going to be the key vector for every token. So here, each row is the query, and here each column, because we transposed the matrix, meaning we flipped its rows and columns and essentially put the matrix on its side, so to speak, we have the columns here being the keys. So write key, me key, a key, poem key. And then when we think about what this matrix multiplication is doing, is we have the query for write kind of dot producted with the query or the key for write. And then we have the query for write dot producted with the key for me. And then we have the query for write dot producted with the key for A, and we have the query for write dot producted with the key for poem. And the same thing is kind of done for every other query, right? All the queries and keys kind of get dot producted. And if you recall the dot product operation from linear algebra, the dot product operation is supposed to be a measure of how similar two vectors are to each other. I'll have a separate explanation for that right after this clip, which you can jump to. But if we take the query for every vector, remember every vector is emitting a query and every vector is emitting a key. Well, if we dot product them, that's kind of like saying, okay, if this is a gauge for how similar they are to each other, then the tokens whose queries and keys match up, maybe the query for write matches up with the key for poem. Or using the character example we talked about earlier, maybe the query for Q matches up with the key for U. If those match up, then we can say those tokens are important to each other, and we would have a higher number coming out of the dot product. And if we see what shape this tensor is after you do this multiplication, we can actually see that the t by a multiplied by the a by t would give us that t by t tensor, which we were looking for. So q times a transpose, specifically q, which is the output of that trained linear layer, k, which is the output of the trained linear key layer, gives us this t by t attention scores, which we were looking for all along. So let's give a quick explanation on why the dot product represents how similar two vectors are to each other. Remember, when we're doing that matrix multiplication, that's what we're doing. We're doing a dot product, this row times this column. So that ends up being this 1 times this 0, and then we go in and do plus this 0 times this 1. Well, for these two vectors, in this example, their dot product ends up being 0. And if you were to graph them or plot them, you see that they're completely perpendicular to each other. They're not pointing in the same direction at all. We would say they're completely orthogonal to each other. This is kind of different than these two vectors over here. Let's imagine that this is the query for a token, and this is the key for a token. And we're trying to figure out how similar these are to each other. These at least they're partially in the same direction. They're not, completely orthogonal, completely pointing away from each other like this one. So here, if we had, say, 3, 2, dot producted with one of them being 2, 3, we're getting some number like 12. And that's obviously much farther away from 0, kind of indicating that these two vectors do share some kind of similarity. So that's why we're actually doing the query times k transpose, the query times k transpose, and that's why that gives us the t by t scores. Okay, so we just have one or two things left to explain. In our t by t tensor that we have generated, the next step, if you remember that attention formula that I showed at the start, is to actually apply softmax to it. And you can kind of think of softmax as a multi-dimensional sigmoid. So it'll squash everything to be between 0 and 1. So we can see that being done over here. It's between 0 and 1 now, between 0 and 1 now, between 0 and 1 now, and between 0 and 1 now. But the way the formula works, the way it kind of raises everything to the power of e, and that's to make it positive, by the way, and not negative anymore. And then we divide by the sum of the entire vector. Not only does it squash everything to be between 0 and 1, but it'll make everything sum to 1. So all of these numbers will now sum to 1. And on our t by t tensor of attention scores, what we do when we apply softmax is every row is now going to be between 0 and 1, and every row sums to 1. So we can kind of think of it as given say a given row, which corresponds for a given token, and then all the columns going left to right, if those sum to 1, we can kind of think of those as scores or maybe even probabilities that that token might be relevant to the token corresponding to the row. So again, not super important to worry about the mathematical details of softmax, but it is nice that it would normalize our values and squash everything to be between 0 and 1 instead of having like totally random numbers like we did in the previous tensor we showed, where we had a number like 73 and like 96, and then, just a totally arbitrary range of numbers. So once we have those normalized t by t scores, to actually get the output of this attention layer, why do we multiply it by v, something called v, instead of just multiplying it by the input like we originally did when we were doing the example with all of the 1/4 in the matrix? So in addition to how every token will emit a query and a key, every token is also going to emit a value, and this is going to be another vector of size dim att, or attention dim, that every vector is going to emit, and it will be learned and trained with a linear layer. And the reason we do this is to just kind of add another level of complexity to the model, because if the query is what the token is searching for, if the key is what the token actually has, and well, let's say the value is actually what is the token actually willing to share, because there are various pieces of information associated with every token, right? That's in the key, but the value, not the Q, not the K, but now the V, the value is, okay, what information is actually relevant? What information do I emit in my vector? Do I actually want to share? We don't necessarily want to share the entire unmasked input, right? Like doing t by t scores times the input. Instead, we'll multiply it by v, where v will be learned. So then the model can actually learn, okay, for every token, what information is actually relevant to share with the other tokens. So that would be the value. What the token is looking for is the query. What information the token has, which should be kind of matching up with the queries for other tokens, is the key. And what information it's actually willing to share is the value. So the last thing we need to explain is why did we divide by the square root of dk before we applied softmax, where dk is the attention dim. That's what dk actually is. This is actually something that you'll find in neural networks and deep learning all the time. The researchers kind of experiment around with different scale factors. We're just dividing by the square root of dk, which is a single number here, no matrix multiplication or matrix divisions or anything like that. But often neural networks can suffer from something called an exploding gradient or a vanishing gradient, where the values of the derivatives during training get either way too big or way too small and things kind of become unfeasible. So it's often better to kind of scale down or scale up our values by some sort of scale factor, which is exactly what we're doing here. And the researchers who created self-attention, they were researchers at Google in 2017, they actually found that this achieved far better results, and it's kind of become standard when coding up self-attention. And the operator that I've been using here, by the way, is matrix multiplication in PyTorch. So now you're ready to code up self-attention. Let's solve self-attention. We're finally ready to code up this super important component of transformers. And I'm going to highly recommend that you check out this video for an explanation of the concepts, though I will definitely explain the concepts, give an overview of them in the solution video as well. And similarly to how we first learned linear regression, we implemented it from scratch, and then we unlocked the nn.linear class, which we simply use as a building block in neural networks. It was specifically used extensively in the handwritten digit recognition. It was used in sentiment analysis. It's used in many neural networks. So now that we're on our journey to actually coding up this transform architecture that makes up GPT, there's a whole bunch of new layers that we're going to need to talk about. nn.linear is a component of GPTs, but there's some other layers in this really complicated looking neural network architecture that we're going to break down and make simple. And mainly, actually, one of the most important components of the GPT and transformers in general is self-attention. We can see it appears here and it appears here. And it's one of the most powerful components of a transformer. It's actually the thing that makes transformers very unique compared to other neural network architectures. So by this point, I will assume that you have solved the GPT dataset problem and are generally familiar with the input that we pass into these GPTs during training. It's actually just a sequence of tokens or words, and there's actually many training examples embedded within even one sentence. This model during training is just learning to predict the next token over and over again, given a bunch of contexts. So in this sentence, if we were to say pass this in during training as one of our sentences in a batch, the model can actually learn that given a context of write, me comes next. Given a context of write me, A comes next. Given a context of write me A, poem comes next. So as information is actually flowing through this neural network, all culminating in the model's prediction for the next token, which we'll talk about this later, but it ends up being a bunch of probabilities for all the possible next tokens. And then we may do something like take the highest probability, or we might do something more complicated, just depending on the scenario. There's many neural network layers that factor in to the model's prediction of what is the next token in the sequence. And one of the most important layers within this neural network that helps the model achieve that is the attention layer. And I'm going to talk about a little bit before we get into the attention layer, actually what happens before the attention layer. So we can see that there's actually some sort of embedding layer over here. And this is exactly the same embedding layer that we used in the sentiment analysis model. So given a vector or a sequence of tokens of length t, here we can say with write me a poem, capital T equals 4. For every token, we're going to get an embedding or feature vector, which should encapsulate the meaning of that word or of that token. And this is actually learned through training, through gradient descent. And let's say our embedding dimension that we choose is capital E. Now our input of size capital T has now become T by E if for every token we have a vector of size E. And this T by E tensor is what's going to be fed in to the attention layer over here. And what the attention layer outputs is actually something of size T by A, where A is not the embedding dim, but actually the attention dim. So we can see now for every token at every single time step, here's one time step in the sequence, here's the next time step in the sequence, we can see that for every single token, we have a different vector now. And this vector may or may not be of the same size depending on whether or not A equals E, but that's actually not the important thing. The important thing is that this transformed vector vector that we have for every token now contains a slightly different piece of information. It actually is now a transformed version of the vector that encapsulates what the model needs to attend to or focus on, what's actually important for the model to pay attention to. That's where the term self-attention comes from. And this transformed vector, the way that the self-attention layer works inside here, the way we're generating this vector of what the model should pay attention to for every token is actually by aggregating information from the other tokens. So let's say the model has now a new representation for the word me. Well, the model has factored in everything that came before me, factored in all those other tokens and aggregated that information together to have a new transformed representation of this token, which represents what the model actually needs to pay attention to. So now let's dive into how that actually works and make this a bit less abstract. Before we dive into exactly how attention works, let's just make sure we're clear on everything in the problem description. The forward method will return a batch size by context length. Context length is the capital T that I was just talking about by attention dim tensor. And we can see that the input dimensionality is actually the embedding dim. So the input would be B by T by capital E. And we're also given the attention dim, which is like the capital A that I was just talking about. People also call this the head size. We don't really need to worry about the word head right now. That's actually going to be explained more in the next problem where we talk about multi-headed attention. And then third input that we receive is the actual B by T by embedding dim tensor, which is the input to the forward method for this self-attention layer. Again, we are actually coding up the self-attention class, which will simply be used as a layer later on in the GPT class, just like NN.linear. So in the constructor for the self-attention class, we'll define the relevant, the instance variables and the layers that make up the self-attention class. And then the forward method for self-attention will be just like getting the model's prediction for that layer, passing in the B by T by E input into that layer, and it returns the B by T by attention dim tensor. And just to make sure that's super clear here for this input tensor, we can see that we have two different 2 by 2 tensors. So this is like 2 by 2 by 2. So this is B by T by E. So you can actually see that capital T, or the context length, is equal to 2 in this case, and the batch size is equal to 2, and capital E equals 2. So then this one should be 2 by 2 by 3, since 3 is the attention dim, the batch size and capital T, or number of tokens, remain the same, and we can see that that is the shape of this tensor over here. And the numbers might feel a bit meaningless right now. This example is more just to help you understand the shape of the inputs and outputs. So the numbers might feel a bit meaningless right now, but they will make sense soon once we explain how self-attention works at the lowest level. Let's build some more intuition for how this works with a simple example. Let's say we had a sentence like dog is cute that we were feeding into GPT. And again, we don't really need to worry about the inner workings of GPT for now and that complex transformer diagram. Let's just build some intuition for how this concept of self-attention works. And let's just say B equals 1 so that we are only dealing with one example at a time. We're not processing like other sentences in parallel in this batch. So T equals 3 if we're doing a word level breakdown of the sentence. And let's say E equals 2. So every token would be represented with a vector of size 2. And this is our input X. That is kind of that T by E tensor that is fed into the attention's forward method. And we can see that the first row is for dog, the second row is for the word is, and the third row is for the word cute. So let's say we had these embeddings learned by the model, and let's just take them to be like what they are at face value. Let's not worry about where these numbers came from, just that this is the model's learned representation of these words. And this will make sense soon. So if we wanted to plot them, we can see that dog is over here, is over here, and then cute is over here. So then the way self-attention works, the way it actually then represents or generates this new tensor of size T by A, where now we have this transformed vector, which has the important information for the model to look at for every single token. The way that this is generated is the model considers a T by T, or it actually generates a T by T tensor. So you can think of this as a tensor of scores or weights, right? If we have T tokens and we look at a T by T tensor, then that is like T squared entries, right? So we're considering every single pair of tokens, every single possible pair of words and we're matching them up. And in this tensor, if you were to index it at, say, row I, column J, where row I is corresponding to the ith token and column J is corresponding to the jth token, the way we interpret this, and by the way, we're going to make these numbers be between 0 and 1, is we're actually going to interpret that as a score of how important those words are to each other in the sentence. So in the sentence, like dog is cute, you might imagine that the row for dog and the column for cute, we might have like a really high number because cute is important for describing the word dog in that sentence. So this would be like a number or a score between 0 and 1 being more important, 0 being not important to each other at all. And this is going to be a t-squared sized tensor, which contains the scores for every single pair of tokens and how important they are to each other. How strong of association do they have with each other, and how important are those pair of tokens for actually understanding and processing the meaning of the input. So for now, let's not worry about the exact formula that the model uses to generate this t by t tensor. We will explain that in a bit, but let's assume that the model did generate this t by t tensor for the input dog is cute. And let's just understand what's in this tensor. So we can see that for dog, so we can see the row 1, column 1, dog and dog has some like relation to each other, right? It's the same word. So we'll see that for is and is, cute and cute, I just put the same number, 0.7, because obviously a word is important to itself, right? That these diagonal entries are kind of meaningless, but the model will still learn some sort of number for those entries. The more important entries to focus on are the ones not on this diagonal. So we can see that for row dog, the future tokens that come after dog, like is and cute, are actually completely zeroed out. And this is intentional. And you may have heard of something called masking in self-attention. It's okay if you haven't heard that term before, but essentially what this means is if the whole goal of these models is to predict the next token in the sequence, then we shouldn't be letting the model during training look at those future tokens. If the goal is to predict that is cute comes after dog, then why would we let the model look at these future tokens? We're completely going to zero out those attention scores. Instead, for every single token at every single time step, we only let the model see the current time step and everything that came before it. So if we look at the second row, which is for is, we can see that the word that came before it, dog, 0.5, right? It has some importance to the word is, dog and is. Obviously, it's kind of like a helping verb in this sentence, but maybe not like crazy important. Then obviously is important to itself, and then we don't let the model look at the future token of cute, which comes after is. This is a really important entry in the matrix though. Dog comes before cute, right? So for the row cute, we're considering all the other tokens that came before it, up to and including cute. And we see a really high number here. This makes sense, right? Cute is actually the adjective describing dog in the sentence. For the model to truly understand the language and meaning of this sentence, the model needs to realize that this pair of tokens, dog and cute, are very strongly associated with each other, hence the value of 0.9. And then, of course, maybe 0.5 for is. It's just a helping verb that kind of links dog and cute, so we just have a 0.5 there. So we'll talk about how the model generates this t by t tensor. That's one of the biggest parts of coding up the self-attention class in a bit, but we just want to understand the whole value of having this t by t tensor first. So now let's explain how the model uses this t by t tensor to actually get the output. Here's on the right is going to be the output of the self-attention forward method. So here on the left matrix, we actually have that t by t tensor over here. And here, what we have is the actual input. This is that t by e tensor, which is the embedded vectors for each token. Each row represents a time step in this tensor. And then what if we matrix multiply them together? What would that actually give us? And again, this is as deep as kind of like getting into the actual like matrix multiplications we're going to go is. This is just kind of the one time we're going to really look at it, is it really does help with the understanding. Won't do like any crazy unnecessary math. So we have this row here, 0.700, and we multiply that with this column over here, which ends up getting us this entry over here. So we have the dot product of those two vectors, and that gets us 0.7 over here. And again, let's look at this matrix over here. It's technically, we said the output was t by a. Let's just say a equals e in this scenario. So the output is still t by e or t by a. And so each row here is also a time step, and this is dog is cute. So the vector here should be like the transformed version of the word or the entry for dog. And this transformed vector should actually contain the information that we need to pay attention to. So let's try and understand what this multiplication was actually doing. We have the scores here for how dog is relating to all the other tokens in the sequence. And this vector over here is essentially the first column of every single row in our feature vectors or embedding vectors, right? So this entry over here is like kind of half the representation of the word dog. Of course, we're not including this column over here. This is part of the representation of the word is. This is part of the representation of the word cute. And the score for dog is being multiplied with this thing for dog. The score for dog is being multiplied with, the number for is. The score for dog cute is being multiplied with the number for cute in this column over here. And remember, our goal is that we want this new vector for every token/row to actually aggregate or factor in the information from the other tokens, right? Because for the model to, again, truly understand text, the model needs to understand the relationships between the different tokens in a sentence, right? We know that we can't just be looking at these words independently. Rather, the model needs to actually understand the different relationships between the tokens in a sentence. However, when we say aggregate or factor in information from the other tokens, we really only mean the information from the tokens that came before and like up to including the current token, right? We don't want to let the model look at the future tokens. So if we actually see what's been going on here for this first row for the new transformed version of dog, if we actually do the matrix multiplications, so then we have the same row again over here times this column, we actually just end up with 0 over here. So it doesn't seem like a drastic change for dog. We just have 0.70. But what this actually is representing is that, well, dog is the first token in the sentence, right? So that's why we have these zeros over here. Dog wasn't even allowed to look at the future tokens, which is why it doesn't seem like we really factored in much from the future tokens. Let's not worry too much about this second row over here, since it's probably not going to give us a ton of important information. As we saw earlier when we were looking at the scores, that is was not like a super critical word in this sentence. However, the relationship between dog and cute and the effect of having this 0.9 in this entry of the matrix over there is about to become apparent. So let's say we are trying to generate this third row over here. So we know that is done by taking this row over here and multiplying it with this column over here. So we get 0.9 minus 0.5 minus 0.7. So if we take a look at the effect of that, this 0.9 is much larger than 0.5 and 0.7, and that 0.9 gets multiplied with this entry for dog, whereas these smaller weights over here are getting multiplied with the entries for these other tokens over here. So in this sum that actually becomes this entry over here, the effect of dog and cute, this score or association of 0.9, is weighted far more heavily and is actually contributing far more to this overall sum rather than these other terms, which are actually bringing this number down. And if you actually finish out the matrix multiplications, you'll end up, when you actually plot those new vectors for each token, this is what we end up with. And it might seem like a pretty small change. We'll notice that dog has shrinked a bit. We'll notice that is has actually shifted a bit, and cute has shifted a bit. And this might seem small to us, these numbers, but this is actually helping the model learn the relationship between all the tokens inside the model and ultimately make its prediction for the next token in the sequence with the final layer of the model. So how is that tensor of t by t scores actually generated? If you look up the formula for self-attention, you're going to see something like this, which seems a little ugly, but it actually has an intuitive understanding or an intuitive explanation. So we said we wanted to consider every single pair of tokens and how important they are to each other. Well, the way the model achieves that is by actually breaking down these, invisible barriers between the tokens. And now instead of processing the tokens independently, it starts letting the tokens talk to each other. Attention is actually a communication mechanism between words. And that sounds a little crazy at first, but what I actually mean by that is that for every single token in the sentence, we're going to emit two vectors. The model is going to generate and learn two vectors for every single token. And one of those vectors is called Q for query, and one of those vectors is called K for key. And the query actually represents what the token is searching for or querying for. I am a token, so the token is talking to other tokens, it's generating a query vector, and the token is saying, okay, I am a token, here is what I am looking for. if you meet me, hopefully if you meet what I'm looking for, my criteria, hopefully we can meet up and then get a high number or a high score together in this tensor. So what I actually mean by that is a noun might be searching for an adjective to describe itself. So the query for dog, this vector might have similar information that is actually embedded in the vector for cute, because we know that is the adjective that describes dog. So we actually are going to look at all these queries and keys and see which ones match up. So the key, if the query is what information the token is searching for, and that is emitted by every single token, then the key vector emitted by every single token represents what information that it actually has. What information does that token actually contain? So the query for dog might match up with, say, the key for cute, since we know this is a noun, we know this is an adjective, maybe they're looking for each other. So every single token is going to generate a key and a query. So if for every single token we have a vector, and that vector will be of size A, size attention dim, then the query tensor or the query matrix is T by A. Same thing for the key matrix or the keys, that would be T by A. So then if we actually multiplied Q times A times K transpose just means to swap the rows and columns in a matrix, then that's a T by A, this is Q, multiplied by an A by T, this is K. So then the A's are actually going to cancel out. This makes the matrix multiplication dimensions work out, and we end up with something that is actually T by T, which is actually exactly what we wanted. And then if you actually kind of take a look at an example and see like the row for a query being multiplied with a column in K or K transpose, you'll see that that's literally aligning the queries and keys, because we want to see which queries and keys actually match up, right? We want the queries for maybe say a dog to match up or actually align up with the vector that represents the key for cute, and then that dot product of those two vectors is some sort of number that's stored at entry ij in this T by T tensor. So maybe I is the row for dog and j is the column for cute. Or actually, as we talked about earlier, that entry would be maxed out to be 0 because we wouldn't let dog look at future tokens. So it might be more accurate to say the row for cute, maybe I corresponds to cute and j corresponds to dog, right? It would actually be the row for cute and the column for dog. And then that number, that dot product of say that query and that key is a number in this T by T tensor, which represents the score or association between dog and cute. So then what is this little scale factor that's square rooted in the denominator over here? This is just one of the contributions from the 2017 paper, Attention is All You Need, and they actually introduced this idea of scaled attention. So dk, or the dimensionality of k, is actually just this attention dim, the capital A or head size number that we talked about earlier. And the researchers found that when you actually divide this q times k transpose, we know what that represents. That's our T by T tensor. But then if you scale it by dividing by the square root of dk, you actually end up with a much smoother training process, and you won't run into any extreme values or extremely small or large gradients, which makes the training process a lot easier. So this part of the formula isn't as important for our conceptual understanding, but this part, q times k transpose, is definitely really important to understand. One additional thing we're going to do to actually ensure that all our entries in that T by T tensor are between 0 and 1 is we're going to apply the softmax function. And the softmax function is kind of like a multi-dimensional sigmoid. We talked about the sigmoid function earlier in these problems, these ML problems, as a function that makes anything that's inputted into it be between 0 and 1. And the higher the input is, the higher the number is to 1. The lower the input to sigmoid is, the closer it is to 0. So softmax is pretty similar, except it'll also make all the entries in your vector that you apply softmax to. Not only will it make every entry between 0 and 1, but it'll make them sum to 1. So we're actually going to apply the softmax function to each row of this T by T tensor. We're going to apply the softmax function to each row. So then every single entry in this tensor will be between 0 and 1, and each row would also sum to 1. So if I looked at the row for dog, right, the row for dog and the columns are like dog is cute, then this actually is going to force all of these numbers to actually sum to 1. And we like that because then we kind of think of this as a probability. because we know all the probabilities have to sum to 1. So we can actually think of it as, we can think of ij as like the probability that the ith token and the jth token are important to each other. Clarify exactly what we mean by softmax is, let's say we had some vector here, 1, 2, 3. To apply softmax to this vector means to actually raise every term in the vector to the power, e to the power of whatever that is. So e to the power of 1, e to the power of 2, e to the power of 3. And then all of these entries in the resulting vector are divided by the same thing. That's what makes everything be between 0 and 1 and actually sum all the way up to 1 when you actually add up all of these numbers over here. So represented in a formula, the softmax at entry I is just e to the xi, where xi is, say, the entry at the ith position in our vector, which we can call x, and then we divide by the sum of all these e to the xi's. That's kind of an ugly looking formula, but here's what it would look like as an example. And in the code, since you want to make in our, let's say that's a b by t by t tensor that we're actually applying softmax to, right? The whole time we've been talking about a t by t tensor, but that's just for one example, right? If we're processing examples independently in a batch, then for every example, there's a t by t tensor. So just to be really clear, when we actually want to apply softmax to this, we want to apply to softmax to every row of the t by t tensor, but for every batch. So the way you would do this in code is nn.functional, this is the function that we use to call softmax, dot softmax, and then what we're actually going to do is pass in the tensor. So let's just call this scores. These are our scores. So you'll go ahead and pass in scores, and you'll go ahead and pass in the dim. And the dim, since we have a three-dimensional tensor, is either 0, 1, or 2. But since we actually want to make each row of this t by t tensor for every batch sum to 1, you're simply going to pass in dim equals 2. One final thing before we're ready to talk about the coding. So the forward method is actually going to return the softmax of our scores, that's this first factor that I've just underlined here, times v, which is our value. Earlier, when we were doing that first dummy example where we multiplied our 2 by 2 t by t scores times our input, the b or t by e input, I essentially said that we were doing our scores times what we can call x, the input to the forward method. But that's not actually what's done in practice, and that might have been why the numbers looked a little weird. So what's actually done in practice is for every single token in a sentence, so let's say we have a sentence like dog is cute, for every single token, for every single word, not only do we emit a query, not only do we emit a key, but for every single token, I'm only drawing it for dog, but it's also the case for every other token, we're also going to emit something called a value vector. So if the query is what the token is searching for, the key is what information the token actually has, the value will also be another learned vector for every token that will be generated. And this is what information does the token want to share? Because there might be a whole bunch of information, right, in the key. There's a whole bunch of information that a token has, but maybe not all of it is actually relevant to share with the other tokens. So when we actually do our t by t scores multiplied by, our input, and actually that gets us our aggregated output, we actually are going to multiply by v, where v is t by a as well, just like q and k. However, every token is going to emit a vector of size a called the value, which represents what information is actually relevant to share. Now we're ready to talk about how to actually code this up and the implementation details. So nn.linear is going to be our friend again. In order to generate our keys, queries, and values, we're going to have in our constructor for the self-attention class 3 instances of nn.linear. One of them for generating the keys, one of them for generating the queries, and one of them for generating the values. And you can imagine that in features would be the embedding dim or E, and out features would be the attention dim or A. Next, when we actually matrix multiply Q and K in the self-attention formula, this at operator in PyTorch actually does matrix multiplication, or you can use torch.matmul. You can actually check the Torch documentation for that. You're actually going to want to do Q matrix multiplied, so at operator, times torch.transpose, and then pass in k, and then you're going to transpose the first and second dimension. So that will actually give us the b by t by a tensor, which is q, matrix multiplied by the transpose version of k, which is b by a by t. So the reason we're transposing the first and second dimension is because originally it's b by t by a for the k, the keys, but we want to switch the a and the t. Remember, this is dimension 0, this is dimension 1, this is dimension 2. So if we swap those, that gets us the matrix multiplication that we actually want. It'll do the batches, it'll preserve this batch dimension as kind of like a parallel processing independent leftmost dimension. And then for every single pair of batches, we're doing the t by a times the a by t, and we know a t by a times an a by t gives us the t by t that we want. Another thing is, how do we actually do the masking that we talked about earlier? The best way to actually implement this is to use torch.ones and pass in capital T, which will give you a tensor of all ones, which is of shape t by t. And then you can pass that into another function called torch.trill, which is actually short for lower triangular or something like that. It's some linear algebra term. And then this is going to give us this tensor over here, which actually has, the future tokens masked out. And then we can maybe store that in a variable called pre-mask, because what we're actually then going to want to do is, let's say we have our scores, right? Scores is actually, after we've applied Q times K transpose and we've done our division, that divided by square root of dk. Let's say that is the state of scores at this point, but it's before we've applied softmax. We're going to actually want to do the masked fill on scores before we apply softmax. We want to get rid of those future tokens for every single time step before we apply softmax. Otherwise, then in the softmax, if let's say you were to zero out the scores for those future indices after applying softmax, well, then for the ones that are not zeroed out at every single row, right? Because of how the softmax formula works, where it's doing like e to whatever's in the first entry, e to whatever's in the second entry, even if you later mask those out, the denominator was still factoring those in, right? So you want to erase those future tokens contribution before you apply softmax. And the way you'll do that is with scores. You will simply call the masked fill method from PyTorch. And then in the first entry, you want to pass in a mask, which is just, a tensor of trues and falses. So you would say pre-mask, which is just this tensor over here, equals 0, which would get us, the trues and falses, the trues where we actually want to do the masking. And then at those entries, you want to pass in negative infinity. And the reason you want to pass in negative infinity is because then as a result of softmax, then after you apply softmax, you would get 0. And let's explain why that's the case. So just a quick math review on why this is the case. Again, this is probably as deep as the math is going to go. When you pass in that negative infinity, or whatever like the lowest value in Python is, into the e function in the softmax formula, well, e to the negative infinity is like 1 over e to the infinity. That's just an algebra rule. And then e to the infinity, if we think about what the e function looks like, it's like an exponentially growing function like that. So as e is approaching infinity, this function is approaching infinity, right? So I can just replace 1 over e to the infinity with infinity, and this is just 0, which is exactly what we wanted. We didn't want those future tokens to have any contribution. We wanted to zero them out. And the way to zero them out is to actually set them to negative infinity before you apply softmax. So why is 1 over infinity 0? It's just a quick review from maybe calculus 1. So 1 over 2 is a half, 1 over 5 is 0.2, 1 over 10 is 0.1, 1 over 100 is 0.1. As this denominator is getting bigger and bigger, the numbers are getting smaller and smaller, so 1 over infinity is essentially 0. Okay, now we're ready to code it up. So we know we're going to need 3 linear layers, each one for generating keys, queries, and values respectively. So we can say self.getKeys is nn.linear, and then, the in features for the vectors or tensors passed into nn.linear there are going to be of size embedding dim, since for every vector originally we have for every token originally, we have a vector of size embedding dim, and we want to get for every token then a vector of size attention dim. And then similarly, we might have get queries is nn.linear of the embedding dim, and then the same thing, attention dim. And then again, the same thing for the values, right? nn.linear, embedding dim, attention dim. And those are actually the only instance variables we need here. Just a small adjustment. Remember, we don't use biases in the linear layers for getting the keys, queries, and values. In linear regression, when we're doing W1 times X1, W2 times X2, W3 times X3, at the end, there is an optional constant term B called a constant term since it's not actually being multiplied by any of our input features, right? We're just adding it as a constant. And it can optionally also be learned through training, through gradient descent. But if we pass in bias equals false, this will not be included. We'll simply have our W's times X's. And in the case of self-attention, it's actually been found that we can get slightly better results without the bias. So there's no need for a bias here. So now let's actually use those layers to get our queries and keys and values. So we can say K is self.get keys of the embedded version of our input. So if embedded is B by T by E, this is B by T by A. Similarly, Q should be self.get queries of, again, embedded and has the same dimensions. And then the values, self.get values of embedded, and again, same dimensions. So now we actually want to do the matrix multiplication, right? We have to do Q matrix multiplied with K. That's how we actually align the queries and values and see which ones match up. So I might say scores is Q matrix multiplied with torch.transpose of K. And again, I want to swap the T and the A. So I would say 1, 2. It'll also work if you pass in 2, 1. So 1, 2. And then we also are going to need the value of the attention dim, right? As we know, we actually are going to want to take the square root and divide by it, right? So we can actually get the attention dim from a variety of places. The easiest place to get it is just K, right? So you know it's B by T by A. So we can just say B by T by A is K dot shape. So we're unpacking that whole dot shape tuple. And then here is when we can do our scaling, right? So you can actually say that scores is equal to scores divided by the attention dim, which is just A square rooted. So now we have scaled the scores. Now we want our lower triangular tensor. So we'll do something like torch.trill, just like we talked about earlier, on torch.ones of T. And then maybe this is our pre-mask that I talked about earlier. That's before we actually get the tensor of trues and falses. That would be like the true definition of a mask. And then we might say that our true mask is simply pre-mask, but we want to look at the entries where this thing is equal to 0. And then we can say something like scores equals scores.masked fill. Go ahead and pass in the mask, and then Python's version of negative infinity or whatever like the smallest system value is. So that would just be float of negative infinity. And now we can actually apply softmax. So we can say something like scores equals nn.functional.softmax, pass in the scores. And again, here is where we want to say dim equals 2, because scores is B by T by T, but we actually want to do this for every T by T. And then given a T by T, if you wanted to say set every row to sum to 1, right? You're trying to apply softmax to every row. That's going across the columns. So it's actually that final dimension over here, dim equals 2. And now that we have the scores, we can actually use them to actually get our transformed output. So we would go ahead and say something like transformed output is simply scores matrix multiplied with our values. And then we can simply round this. So return torch.round of transformed and say decimals equals 4, and we're done. And we can see that it works. I hope this was helpful, and definitely leave a comment if there's anything that you would like me to explain in more detail. There's definitely a ton of concepts embedded within coding up this class, and we're a few problems away from having a working GPT from scratch. Okay, in this video, we're going to explain multi-headed attention. multi-headed attention. And as you can see from the transformer architecture, which you may have seen before, is one of the most important parts of the model. It actually occurs over here. We actually won't include this part of attention right here, since that has to do with the encoder, which I've actually cropped out of the diagram. Large language models like GPTs don't use encoders, but attention, specifically this masked multi-head attention, and we're going to really focus on explaining the multi-head aspect of attention in this video, is one of the aspects of the GPT that makes it so powerful. It was discovered in 2017 by researchers at Google, and we're going to break down exactly how it works. But before we break down multi-headed attention, let's do a quick breakdown of how single-headed or just normal attention works. So when ChatGPT or any language model receives an instruction, like write me a poem, we know this is something that ChatGPT does pretty well on. Well, the model actually needs to know what parts of this sentence, this input sentence, to focus on, specifically to pay attention to. Not all of these tokens are important, right? Obviously, the more important ones in this sentence are write and poem. Imagine if you just said write poem to ChatGPT. It would still understand what you're doing. Or understand what you're requesting. That shows us that these are the two most important tokens, and the model needs to learn to pay attention to these when it's given a real sentence, like write me a poem. And this is actually what attention solves. So this is what the attention layer solves. It's actually a layer in a neural network that will take in. Here's what it will take in. It will take in the embedded version of a sentence. So the first step in any kind of language model is to actually tokenize the sentence. So we'll break up the sentence into tokens, and for now, let's just assume we're using a word level tokenizer. So we have some sort of matrix that is actually going to represent this sentence, or a tensor in PyTorch. And we're going to say this is T by E. And the reason it has T rows is because we have T tokens in every sentence. If we break this down on the word level, we'll have 4 tokens here. So we would actually have 4 rows here. And then E is actually something called the embedding dimension. The embedding dimension. Let's just assume an embedding dimension of 2. Then we know our matrix or tensor looks something like this. And the embedding dimension for every single token, so for write, for me, for A, for poem, this is going to essentially be a vector that encapsulates the meaning of the word. So you can think of it as a feature vector that summarizes the information in that word in a way the model can actually understand. And that will actually be learned through the process of training a neural network. But what the attention layer outputs, right? This is just what the attention layer takes in. The attention layer is actually going to output a tensor that is, instead of being T by embedding dimension, the output tensor is actually going to be T by attention dimension. So T, we can call this A for the attention dimension, also sometimes called the head size. And this is also technically going to be a vector for every token, but it's going to be a transformed vector that kind of encapsulates the relevant parts of the token that the model actually needs to pay attention to. So if I had to summarize attention in just a couple sentences, it's actually a communication mechanism. Attention says we don't want to look at each token in a sentence completely independently. We want to kind of break these walls. We want to let the tokens talk to each other. We want to let them talk to each other, and we want to let them actually have some time, specifically through the attention layer in a neural network. And we want to let them match up with each other until the tokens that are actually relevant to each other have paired up, right? Because every token has some kind of relationship within it, right? The relationship between write and poem is that poem is what needs to be written. The relationship between me and, let's say, write, well, if you remember for grammar, again, not super important, but me is kind of like the indirect object here. The poem is being written for me. So clearly, for a model to really understand a language, it needs to understand the relationships between the tokens in a sentence. So to summarize attention, it is essentially a communication mechanism that lets tokens talk to each other. Okay, so now let's explain what we mean by multi-headed. Let's say attention dim equals 8 and embedding dim equals 4. So then the input to our attention layer, which I'm just calling A in this black box, is a 4x4 tensor. And I'm just assuming T equals 4, using the same sentence, write me a poem. And then the output would have to be 4x8. But what if we wanted to do something called 2 heads of attention, so multi-headed attention? Well, we would have two separate instances of A, where A is doing self-attention. And these heads, or these two separate instances, are going to operate in parallel, completely separately. They'll have their own parameters and weights that are trained. But let's keep output dim equals 8. So if we want to do that, then we're actually going to have to change the attention dim for each instance of A, each head, as they call it, to 4. So that way we can still have this 4 plus 4 equal to 8. But if we have two 4x4 outputs, how do we get the output dim equal to 8? Well, we can use concatenation, right? We know there's a function in PyTorch. Don't worry if you're not familiar with this, but we can actually concatenate two tensors and tell PyTorch along which dimension to concatenate. And we want to concatenate not along the 0th dimension, but rather at the 1th dimension. And that will actually give us a 4x8 tensor. And let's say we had an attention dim of 16, and we wanted to have 4 heads of A. Then each head size would actually be 4, since 4 times 4 is 16. So we call this number the head size, and we can call this the overall attention dimension. So what multi-headed attention is just doing this normal attention, but having a bunch of instances of it operating in parallel. And each of them are going to have their own trainable weights, biases, parameters that are learned through gradient descent. And then we're going to take all their outputs and concatenate it. And that's what the output of multi-headed attention's forward method would be. So why does multi-headed attention actually yield better results in neural networks than just having one single head of attention, but it has the same attention dim as the output dimension when we concatenate all our single heads together? Why does that actually give better results to have these two separate instances of self-attention, or sometimes 4 or 6 or 8? Well, the number of parameters is staying the same, right? The number of weights, or the number of trainable or learnable parameters in the model, is staying exactly the same, right? We know that the queries, keys, and values, if you've seen the video on the lower level details of attention, we know that those are linear layers that are going to occur in each single head of attention for the model to actually figure out the relationships and scores between pairs of tokens. But if we're shrinking the attention dim for each head, then the number of parameters is actually staying the same. So why are we getting better results when we do attention, 2 different heads of attention, one here and one here, and then we go ahead and concatenate the results? Why is that actually giving us better results? Well, if we think about it, each head of attention gets to operate on the input separately. The input, let's say the embedded input, right? That is our T by embedding dim. So T by embedding dim. This is passed in separately in parallel to each head of attention. So each head of attention gets to operate and do a bunch of math on that input tensor. And since each head of attention has its own parameters, each head can actually learn something different. Actually, what we'll find is after language models are trained, each head of attention is actually specialized at learning some component of the language. And actually, when they did an analysis of BERT, and BERT is actually a very popular transformer that Google uses for all sorts of things, such as Google Translate. When they did an analysis on the heads of attention in BERT, they actually found that one head of attention was specialized at looking at direct objects of verbs, and another head of attention was specialized at looking at indirect objects of verbs. So intuitively, we see these large language models, these models with billions of parameters, as essentially having different heads and different components of its neural network that specialize at learning different parts of a language and kind of a grammar. So that's kind of the main benefit of multi-headed attention. We have different heads that can each specialize in learning something different, even if the number of parameters stays the same, whether we do one head or many heads. So that's multi-headed attention. It's actually not a terribly complicated concept, but it is probably, most people would agree, the crux of a GPT. It is the most powerful layer of a GPT, and it is what allows these modern day language models to actually learn English language and actually any language so well. So I'd highly recommend trying to code it up now. And after you do that, you'll actually be ready to code up the transformer block, this giant rectangular block, which you can see in the picture. And then you will almost have a working GPT. In this problem, we're going to solve multi-headed attention. And again, the first thing I want to say is that I highly recommend you solve single-headed attention before we solve this problem. As if you understand single-headed attention, this problem is not that hard. It's actually kind of easy. Single-headed attention, on the other hand, which this problem builds on, is a lot harder just because there's so many new concepts introduced in that problem. So we're going to assume that you've kind of solved that problem, and then this problem isn't going to be that bad. But we'll still generally explain the idea of attention, but we won't go into as much detail as we did in the single-headed attention video. So the problem statement says that this layer is actually what makes LLMs so good at talking like real people. So single-headed attention is pretty good, but when we do this whole multi-headed thing, which we're going to explain in this problem, that's what made like the latest transformer neural networks way better at chatbots that you might have seen in previous years. And I've also made an explanation video of the concepts if you would like to watch that as well. So we have to code up the multi-headed self-attention class and then the single-headed attention class. Essentially, the solution code for that is going to be given in the starter code for this problem, and we're going to actually make instances of this class to solve the multi-headed attention problem. And we're told that the forward method needs to return a b by t by attention dim tensor. So actually returning the tensor of the same shape as the single-headed attention problem. And we're going to be given embedding dim. That's our first input, and this is actually something that we were also previously given in the previous problem. We're also given attention dim. We're given embedded, which is b by t by e. And this was also given in the previous problem. However, this is our new input that we really need to pay attention to, the num heads. This is the number of times that we're going to make an instance of the given self-attention class. And we have this constraint that attention dim mod num heads is 0. So attention dim is a multiple of num heads. And there's an example here. The numbers are not going to make a ton of sense, but it does help us understand the shapes. Our input is supposed to be b by t by e. That's the shape of embedded, and we can actually infer that the batch size is 2 here. The t, or the context length, is also 2. You can infer that from this example over here. And then e, we can find that e is 2, and that makes sense as well, given that we have a 2 by 2 by 2. We have two different 2 by 2s in our input embedded. And if attention dim is 3, and the b and t are supposed to remain the same, then we have two different 2 by 3s. So it's a 2 by 2 by 3, and that is exactly what we have over here. So the shapes do make sense. So what actually is multi-headed attention? So we take an instance of single-headed attention, SHA, and previously we were passing in our input, the b by t by e input, and whatever single-headed attention returned was the output. However, now, depending on what that num heads parameter is, whatever that is set to, we'll make that many instances of self-attention and have them operate in parallel. So let's just say num heads was 3. Then we have 3 over here. And what we'll do is whatever our input was, that b by t by e input embedded, I'm just going to simplify that to x for now. Let's pass x. Let's actually pass x in to all of our heads of self-attention. If I had a fourth one over here, it would also be passed in there. And then what we'll do is we'll just concatenate all of these outputs together, the outputs of each head. So each head of self-attention, each of these boxes over here was able to operate independently and process X and obtain a different output, right? Because each of these layers of the neural network have different, if they're separate instances, they have different weights, right? They're learning different keys, queries, values in those linear layers that make up the single-headed self-attention. And ultimately, they're going to generate something different since, again, they have different numbers, different weights, they're trained separately, even if they're given the same input. So we're going to then concatenate all their outputs together. We can call this the concatenated version, and that is what we would return from the multi-headed attention forward method. And that's it. So then when we have the transformer neural network architecture, and remember, we're getting pretty close to coding up this full GPT class, we're actually then going to use the multi-headed attention class as a layer in this neural network. So then that's going to become one of our building blocks for this giant block over here, which is called the transformer block. So why does this actually work better than just single-headed attention? Because remember that attention dim, which we can call A, mod num heads is 0. So for each head, we're actually making the size of each head, or the attention dim parameter, when we instantiate that single-headed attention object for each of those heads, we're making each of them have a head size of A, essentially floor divide num heads, whatever this integer is. So our total number of learnable parameters in the neural network isn't changing, right? If I were to do just one head with an attention dim of A equals 64, and the other option is to maybe do 8 heads, and for each of them set A equal to 8, then the total number of learnable parameters in the neural network hasn't really changed, even though we're having multiple heads that are each operating in parallel, right? Each of them gets to process the input, process that input called embedded, and learn parameters, albeit each head is learning less parameters than if we just had one giant head. So why does this actually yield better results? Because the general trend is more parameters, bigger model, the model can learn a more complex relationship, and we get better results. Well, even though each head has less parameters than if we had one massive head, it turns out that each head gets to learn something different, because our input X is independently passed in to each head. So each head independently gets to learn something different. And what we actually find when we see how the heads and those weights get activated based on different inputs is that researchers have found that you'll actually have one head that might specialize in focusing on or attending to the next token. One head that really specializes on focusing or attending to, right? This is all about which parts of the input do we pay attention to, the direct objects of verbs. One head might specialize in indirect objects of verbs. So we know that for a model to truly understand language, it needs to understand grammar, right? It needs to understand the structure of the language and how all the words are put together, or how all the tokens come together. So we actually find that each head specializes in maybe a different grammar rule, and this seems to be why this is boosting the performance of the neural network, rather than just having one head that's responsible for learning all the rules of the language. Okay, now let's jump into the code. So the first thing we need to think about is that we know we're going to have a bunch of instances of this given single-headed attention class. So we're probably going to need to store those in some kind of collection in our constructor over here, right? But it turns out that any instance variables of a class that is a subclass of nn.module, and this multi-headed self-attention class is a subclass of nn.module, any instance variables need to also be neural network parameters. So if I did something like this, self.heads, and then made it a normal Python list, this is going to throw an error when we're using PyTorch because of the restriction that I just mentioned. So there's actually a class called nn.modulelist. So I can say self.heads is nn.modulelist, and it works just like a normal Python list. You can append to it, but it actually is restricted to only store other modules or neural network layers. So then we can say something like for I in range of num heads, we can actually then append those instances. So self.heads.append, and we can instantiate here. So self, we have to do this for these inner classes. We have to refer to it as self. So self.single head attention, and we have to pass in the embedding dim, but then the attention dim for each head is just the size of that head. And we know that should just be attention dim, floor divide, num heads. So now we have all our heads defined. Now we just need to actually write the forward method, actually get all those outputs, and concatenate them together. So we can go ahead and make a list for all our outputs. We can say outputs is just some list. And then we actually want to call the forward method of every head of single-headed attention. So we can actually just say something like for head in self.heads, and we can append to this list. So outputs.append, and it would just be head.forward, or simply just to use the default call. So head of embedded. And now it's just about concatenating those together, right? So we can say concatenated is torch.cat, and torch.cat expects two things. The first thing it expects is a collection of the things to concatenate. So our collection here will be a list, the list outputs, and it expects a dimension, something like 0, 1, 2, etc. So if we think about what the size of each thing in outputs is, right? Each element in this list is b by t by, let's call it head size, right? Because that would be the output dimension from each head of attention over here. And we want to concatenate them along this last dimension so that when I concatenate them all together, it becomes b by t by this overall attention dim that was given as a parameter in the constructor for multi-headed attention. So I would just simply say dim equals 2, or you can say dim equals -1 for the final dimension. Either would work. And then we simply round our output. So return torch.round of catted, say decimals equals 4, and we're done. And we can see that it works. So if you found this helpful, definitely leave a comment, or leave a comment if there's anything else that you would like me to go into more in depth on. Now that we have this multi-headed self-attention class done, we can just use this as a layer when we code up the transformer block in the next problem. So definitely check that one out next, as it's our next step in getting closer to having a working GPT all the way from scratch. Okay, in this video, we're going to completely break down the transformer block. So we're going to explain how every single one of these components works. We'll touch a little bit on the embeddings and the final two layers, linear and softmax, but we're primarily going to focus on explaining the transformer block. So that's the attention, the add and norm, as well as the feed forward. We're going to break these down one by one, starting with the add. Okay, so the add actually refers to a concept called skip connections or residual connections. And here's how it looks visually. We have some arbitrary layer in a neural network. This might be a linear layer. This might be an attention layer. And it takes in some input x, which we can see over here. But instead of just taking the output of the layer as the output, we'll also let some portion of x actually completely bypass the layer, and it will get added to the output of the layer over here. So in code, if we were writing the forward method for some kind of layer and we wanted to incorporate skip connections or residual connections, we would actually return layer of x, so call the forward method for the layer, passing in x, but also add x. And just to get some intuition as to what this kind of means, is the model will actually learn the right weights and biases for this layer so that the right proportion of x is either sent through the layer or the right proportion of x is allowed to actually bypass the layer, right? Maybe we don't actually want to transform x based on this layer. Maybe we want to retain x's original identity and pass most of it, or at least incorporate it into our output for this layer. So the model can kind of essentially through training, through the minimizing of the loss, through the training data, figure out how much of x should be passed through and how much of x should be sent through this layer. That is some of the intuition for what a skip connection is doing. However, why do we actually need to do this addition? Because technically, shouldn't the model just be able to learn the right weights and biases in this layer to not change x at all? Something like this. Why do we actually have to add x to actually get this to achieve our desired results? Well, there's actually another big benefit of skip connections, and it's actually the main reason that they were originally added into these deep neural networks. And that has to do with solving the exploding or vanishing gradient problem. Exploding or vanishing gradient problem, or exploding or vanishing derivative problem. We know that calculating derivatives and gradients during the process of training is very important for gradient descent and minimizing our loss by updating our parameters. However, something that can occur with these super deep neural networks that have tons of layers, left to right, these neural networks have tons of layers, is that gradients can either become super big or super small. And if we recall our update rule for gradient descent, we know that for any weight or parameter in a neural network, the new weight is actually just equal to the old weight minus alpha, the learning rate, times the value of the derivative or gradient. And if this derivative value, if it's too small, if it's vanishing and going basically to 0, then this term is basically going to 0, and the new weight is almost the same as the old weight. So we're not able to update the parameter at all. Similarly, if this value of the derivative is way too large, then the new weight is going to be drastically different than the old weight, and that won't be great for the neural network's performance. So we would like to mitigate this problem in some way or another. And it turns out that this simple addition does end up reducing that problem. Because if we recall from calculus, if you have some function f of x, and it's just the sum of two other functions, g of x plus h of x, when you're actually taking the derivative, you can actually just say that f prime of x is g prime of x plus h of x. So when the model is actually calculating all the derivatives, when we call loss.backward in PyTorch, the model will actually have an additive term when calculating the necessary gradients for this layer. And that actually will significantly help with reducing the problem of the exploding and vanishing gradient. The fact that we're doing an addition instead of a multiplication, as that doesn't drastically compound and, either drastically increase or drastically decrease the value of the gradients as the network gets deeper and deeper. So the short answer is that incorporating some kind of addition seems to actually keep the gradient values from either getting too big or too small. And researchers have found this time and time again with neural networks, and that is why skip and residual connections are included in the transformer. So the norm in the transformer block actually refers to something called layer normalization. And this is kind of a module of its own in PyTorch that you can instantiate by saying nn.layernorm and passing in our case, the embedding dimension. And when you tell a layer norm that you're passing in the embedding dimension, that is the dimension along which we will normalize. So what does it actually mean to normalize in statistics? It essentially means to recenter our data so that it all revolves around the mean. So it will kind of look like a bell curve. And the way that we can take a set of data points and make it have this kind of shape where the mean is the most probable data point, the way we normalize data is for every single data point x, you actually just subtract out whatever the mean is, and you divide by the standard deviation. And that kind of recenters your data around the mean and makes it look like that. However, this would kind of destroy the whole point of a neural network if there was nothing learnable or trainable about this. It's just a direct formula for this layer that restricts the output to be having this shape. So to still have the neural network have some sort of learning capacity, we go ahead and multiply for every data point this minus mean divided by standard deviation. We multiply by some other number, gamma, the symbol is not super important there, and add some other number, beta. And these two will actually be adjustable and learnable across the iterations of gradient descent that we perform. But the question should be, why does this actually improve the performance of neural networks? It has been found to actually increase the training speed of neural networks and make deep learning far more effective. And researchers are actually still not entirely sure why normalization tends to improve the training of neural networks. But their current hypothesis is that we know that the neural network starts off with totally random parameters, right? Totally random weights. And to some extent, our data could be random as well. But if during training there's drastic shift in the nature of the data, meaning it's the two main attributes that characterize data, right? The mean and the standard deviation. If this kind of changes drastically in random ways, then the neural network training tends to be really slow and just not as effective in terms of convergence. So by kind of centering it around the mean, around the standard deviation, this is the standard deviation, and still by adding in some learnable parameters, so this isn't too restrictive, researchers have found that the performance of the neural network does increase, and that's why layer normalization is used in a transformer. One additional thing that I just want to clarify is what data we're actually normalizing. So to feed into this layer, we would have something that's T by E, right? T by E, where T is our time step or length of some kind of sequence, like our sentence, say the number of words in a sentence, and E is something called the embedding dimension. So you can think of that as the size of the feature vector for every token. So let's say for every word, we had a vector that encapsulates the meaning of that word, and that was our embedding vector of size E or of size embedding dim. When we say we are going to do layer normalization, it means we are going to normalize the actual feature, not necessarily the time steps or the batch dimension. If we had, say, multiple examples being fed in and we had batch by T by E, but we're actually going to normalize along the embedding dimension. So for every single time step, we have a vector and we're going to go ahead and normalize along that dimension. Okay, masked multi-headed attention. Let's explain how this works. So during the process of training, let's say we have an example that the model is being fed in. So we have this sentence, write me a poem. So we'll quickly explain what the masked part means. Because this model is always predicting the next token in the sequence, the model actually does not get to look at future tokens. So when the model is fed in a sentence like this, there's actually a few training examples within here that the model can see. The first one is that given write, me comes next. The next one is that given write me, A should come next. And finally, the model sees that given write me A, poem should come next. But the masked part actually means that when the model is making its next token prediction, given all the tokens before it, the model doesn't actually get to see what comes next. So if the model was tasked with predicting poem and the model had the context of write me A, in our code, in our tensors or our matrices, we would actually mask out the word poem so that the model cannot see the answer before it's actually made its prediction. So that's what the masked part means. Now let's explain the multi-headed attention part, which is definitely far more significant. So when the model receives a complicated instruction like this, the model needs to know what part of the input to pay most attention to, because not all words in this input are equally as important. And moreover, there are actually relationships between every pair of tokens. So we know that this pair of tokens, write and poem, there's a strong relationship between them. Because what are we writing? We're writing a poem. The model needs to pay attention to that. We're not writing a book. We're not writing a script. We're not writing a movie. The model needs to know what to write. So this is clearly an important pair of tokens. So what attention does, attention is the model actually letting these tokens talk to each other. And every single pair of tokens will be considered until the model has actually figured out which pair of tokens are important and which ones aren't important. And then the model is actually able to generate some sort of new feature vector instead of the embeddings that were initially passed in. The model is now able to know the important parts of the input to focus on. So attention, if we had to summarize it, attention is a communication mechanism. Attention at a high level is the model letting the tokens talk to each other until the right relationships between them are learned. And the multi-headed component actually refers to the fact that this attention process I just described will actually have the model perform the attention layer on the same input. So we have the same input going into this attention, the same input going into this attention head, as well as maybe further attention heads. We might have 3, 4, 5, or 6, and so on. And what the model will do is it will actually just go ahead and concatenate the output of all the attention heads and pass that in to the next layer of the neural network. So attention is a highly powerful mechanism for the model to gain a deeper understanding of language. And because it's so powerful, we actually want to have many different heads that each learn their own weights and each operate on the input. This head of attention operates on the entire input, and it actually gets to learn its own weights and biases. The entire input is also passed in to this head of attention, and this set of attention learns its own set of parameters. So by exploiting multi-headed attention, the model is actually able to learn and understand language at a far deeper level. Okay, feed forward. Feed forward might actually surprise you that it's extremely simple. Feed forward is just a traditional or vanilla neural network. It's a vanilla neural network. That means there won't be any attention in this neural network. There won't be anything complicated except linear layers. So linear layers with an arbitrary number of nodes or neurons, as well as we'll have some nonlinear activations like the ReLU activation, and we may have dropout as well. But it is still a traditional, fully connected neural network when we do toss in some nonlinearities and some dropout. And it turns out that first having the attention and then having this linear neural network that essentially just does a bunch of computation, a bunch of weights, biases, and a bunch of matrix multiplication that essentially is, remember, just doing linear regression. It turns out that first having computation, first having the communication in the attention layers, and then after these tokens have paired up and essentially the model has figured out which tokens are relevant to focus on, then doing a bunch of computation, essentially a very complex mathematical formula, figuring out those weights and biases after. This is actually highly effective for the model's performance and the model's ability to ultimately predict the next token. So the last part of the transformer architecture, and specifically the decoder, is actually the linear and softmax components. And if you're coding up the transformer block, you won't have to worry about this yet, but you absolutely will once you actually code the GPT class. So the whole point of that final linear layer in softmax is to actually get an interpretable prediction. So for that linear layer, it will actually look something like this. It would be nn.linear of the attention dim. So attention dim, as that's kind of the new dimension after we've done all of this attention after the embeddings. So it would be the attention dim, but that's actually not the most important thing. The output features, or the number of neurons in this layer, should actually be vocab size. And the reason for that is for every single time step that this model receives in, every single token in the input sequence, the model wants to predict what token comes next. And that's going to be a bunch of probabilities, right? So we want to get a vector of size, vocab size, where we can interpret each number in this vector, each entry in this vector, as the probability that the token or character or word corresponding to that index is going to come next in the sequence. And then to squash those numbers between 0 and 1 and actually make them all add up to 1 so we can interpret them as a series of probabilities, that's what the softmax function is for. And that will be the decoder transformer. So if you're following along with the code, you now have the information you need to code up the transformer block class, which will actually, you'll be given the multi-headed attention and feed forward classes. And then you can go ahead and code the GPT class, where you'll be given the block class, you train the model, and then we'll finally code up generate, where we'll finally see our trained language model generate text that looks pretty good and pretty similar to English. So recommend jumping into the code next. It's finally time to code up the transformer class. So this is actually the last class and maybe the most important class that we're going to write in defining the GPT model. So the next problem is actually going to be writing the GPT class, and we're going to use this transformer block class. And this transformer block class that we're about to write is going to make use of the multi-headed attention class that you've previously written. So the transformer block is actually this gray rectangular block that is repeated nx times in this diagram. And this itself is a giant neural network layer that we're going to use in the GPT class. And there is also like a really in-depth explanation on the transformer block over here that explains like layer by layer, breaking down and explaining what every piece of this block is doing. I recommend checking that out. But in this video, we're also going to go over how the transformer block works at a general level, and we're going to code it up as well. And the forward method for this class. So this is transformer block class is going to subclass nn.module, and it's going to have a forward method because we're going to pass some sort of input in to the transformer block and get some sort of output. And it needs to actually return a tensor that is b by t. T is our context length by model dim. Let's just call that capital D. And one thing I want to clarify is that in the previous problems, when we were introducing attention, I kind of made a distinction between embedding dim and attention dim, but they're actually the same thing. There's just one giant parameter called model dim, and they're the same number. And then model dim mod num heads is 0, and then the head size for multi-headed attention is model dim divided by num heads. So let's make some sense of this example. We don't really need to worry about the numbers, we just need to understand the shapes. So the input, we call that embedded, since it's actually the output from the embedding layers of this neural network right before the transformer block starts in the diagram that we just showed. So the input is b by t by d, where d is the model dimensionality, and the output is also b by t by d, the model dimensionality. And we're told that the model dimensionality is 4, as we can tell over here, that we have these 4 columns over here in the input and the output. And then we can actually infer from this that t equals 2, the context length is 2, and we can also infer that the batch size, the outermost dimension, is 2. So now let's jump into how the transformer block works. So one small change from this diagram is that this middle multi-headed attention part, which is actually factoring information from the left part of the transformer diagram, we're not going to incorporate that at all. Transformers like ChatGPT only use this right part of the transformer, which is actually called a decoder, although that term is not super important for now. They only use the decoder and they don't actually include the left part of the transformer at all, so we're just going to completely ignore that. The next thing that we need to actually explain is in the original transformer diagram, they went ahead and described this as add and norm over here, and the same thing over here. but it would actually be more accurate to say norm and add. Researchers have found that norming first and then doing our skip connection or add, and we'll definitely explain what these actually mean in a sec, but norm and add is actually what's done. So let's explain the norm layer. This refers to something called layer norm, which you can actually use as a layer, make an instance variable inside the constructor for the transformer block class, and that's going to be nn.layerNorm, and you simply pass in model dimension. And this is going to tell this layer that whatever tensor is passed in, it's b by t by d, go ahead and do the normalization along this dimension. And what we mean by normalize is when you have some sort of data, to normalize it just means to really center it around some sort of fixed mean and standard deviation. So this is kind of an example of normalizing data. We can see that the data is kind of all revolved around or centered around the mean, the symbol mu. The mean is the most common data point, and the standard deviation just kind of reflects the width and how the data is stretched out from left to right. And researchers have found that this really does boost the performance of transformers. And researchers are actually not entirely sure why layer normalization seems to improve the training of neural networks, but it seems to be something along the fact that we start off with some random distribution of the weights in the neural network, and we don't want them to change too drastically. That actually makes our training process really unstable. So next, let's explain the add, also known as skip connections. And then one additional weird thing that is mentioned in the problem is that the norm is actually going to come before the attention instead of attention before the norm. So now we can actually explain this add in add and norm, also known as skip connections. We have our input to the transformer block X, which is actually going to pass through layer norm, and then the output of layer norm goes into multi-headed self attention, but then we can actually add the unchanged X all the way back to the output of multi-headed self attention, and then this is the output. This is the output of at least the first part of the transformer block over here. This is the first part of the transformer block, and how we would actually do this in the forward method is we would actually just say something like X plus multi-headed self-attention of the norm. Remember, we're going to norm first and pass in X into the norm. And again, this is kind of covered in more detail in the transformer block background video, but the short explanation for why this skip connection over here, actually letting some portion of the input bypass these layers entirely and actually adding X to the output over here, is that having some sort of additive term instead of having only multiplication in this neural network. Having some sort of additive term seems to actually smooth out our gradients and actually slightly mitigate the exploding and vanishing gradient problem during training. So then the output of this first part of the transformer block over here is then passed into the second part of the transformer block over here. And again, we're actually going to apply the norm before the feed forward, even though in the original diagram, it actually says feed forward and then norm. So we're going to do norm and then feed forward and then add this component, which came out of the first part of the transformer block. We're going to add this component back in over here, and that's our second skip connection. So what's the whole point of this feed forward component of the neural network? Well, this is also called a multi-layer perceptron. Multi-layer because we're going to have multiple linear layers and then non-linearities. That's kind of maybe the perceptron part of this term, if you want to think of it that way. It's also called a vanilla or just a standard neural network. Well, if the attention component of the neural network over here is actually our communication mechanism, this is where we let the tokens talk to each other. Again, I highly recommend understanding multi-headed attention through those coding problems before we move into kind of this transformer block problem. But if attention is our communication mechanism, then the feed forward part of the neural network, this is actually our computation mechanism. This is where we have a bunch of neurons in each linear layer of this feed-forward neural network that are learning a bunch of weights, biases, W1 times X1 plus W2 times X2, doing a ton of linear regression. So after we've let the tokens talk to each other, after we've let the tokens do their communication, we want to let the tokens have some time as they pass through these linear layers, and of course nonlinearities like ReLU as well. We want to let the tokens actually do computation, and this is all going to factor in to the model's prediction in the final layer or two where the model predicts the next token. And just looking ahead a bit, this is not going to be part of the code for this problem. It's going to be part of the next problem where we actually code the full GPT class. But just looking ahead a little bit, after the model has done all this communication, all this computation in this transformer block, and then in the GPT class, by the way, the transformer block is going to be repeated some number of times. So we would take the output of the transformer block, pass it back in, and do this some number of times, maybe like 6 times, maybe 12 times. But the point is, after the model has done all this learning within the transformer block, let's actually take a look at what's to come ahead. There's going to be a linear layer where in features is model dim. This should make sense given the dimensions used in the transformer block. And then we're actually going to project to a dimension of vocab size. So this linear layer has vocab size different neurons. We're going to have essentially vocab size different numbers for every single token at every single time step. And the reason we have that many different numbers being predicted is because each number is going to correspond to a probability or the chance that that corresponding token comes next. And we know we have exactly this many different tokens in our vocabulary, so we're going to have the possibility that any one of them could come next in the sequence as this model is learning to predict the next token. So we're actually going to need to have that many different numbers to get the full prediction. So then just to clarify, just looking ahead a little bit as to how this model is going to be trained once we've fully written the GPT class, is we know we had a B by T input, a batch of sequences, each of length capital T. And then, the model, if you saw the GPT dataset problem, I highly recommend solving that problem before doing any of these transformer problems. Well, we know that we have B by T labels because we know that for every context or all the sequences of tokens, the model is trying to predict the next token. So the correct answer or the labels is just actually the tokens kind of offset by 1. And that is kind of become clear in the GPT dataset problem. And then our output is B by T by V for every single batch. And then for every single token, every single time step in this sequence, then we have a vector of size V, the vocabulary size, which we're thinking of as a list of probabilities. The softmax layer over here is going to make all the numbers between 0 and 1, so they actually can be interpreted as probabilities. We have a bunch of probabilities for which token is going to come next in the sequence. That's the model's prediction. And then the loss or error is going to be calculated using 2 things. The model's prediction of the probability for what token came next. Again, that is in this vector of size V. And then we actually know what token comes next. That's in our labels. The labels were extracted from the raw data set, and then that is used to calculate the loss. We drive the loss down during training using an optimizer and following the gradient descent algorithm. And in the end, we actually have a model that can predict the next token really well. Before we jump into the code, I just wanted to clarify one thing. In the constructor for the transformer block class, you will definitely need to make 2 different instances of nn.layerNorm, one for this layer norm and one for this layer norm, so that we can learn different parameters across training. So now let's code this up. We know the first thing we need is our instance of multi-headed self-attention. So we can say self.multi-headed self-attention, and we can use the inner class below. So self.multi-headed self-attention, and the only thing is that we really need to pass in there to this constructor. Well, why don't we check the constructor? For the constructor for multi-headed self-attention, we just need to pass in model dim and num heads as that is visible over here. So scrolling up, we can actually then take a look at that, and we can pass in model dim and num heads. So model dim and num heads. The next thing we're going to want to do is make our first layer norm. So self.first layer norm is nn.layerNorm, and this takes in model dim, the channel or dimension along which to normalize. Then we need our second layer norm, so second layer norm, and that's nn.layerNorm, and again, we want to pass in model dim. And we're also going to need a feed forward layer, right? The vanilla neural network. So we can say self.feedForward equals self.vanilla neural network. This is actually given below if you want to check it out. It's just a couple linear layers with a ReLU function thrown in between. And then we're going to go ahead and again pass in model dim. And that's it for the constructor. Now we can go ahead and write the forward method. So to know that for the first skip connection, or the first part of the transformer block, we just want to take embedded, which is like X that we talked about earlier, and then we're going to do self.attention or self.multi-headed self-attention, and then we're actually going to invoke our first layer norm here. So self.first layer norm, and then to there we are actually passing in embedded. So this does reflect the diagram that we talked about earlier. And then we can save this in a variable called like first part. This is the first part of the transformer block, the part that doesn't have the feed forward layer. And then what we're going to want to head and do is actually take first part and then go ahead and add the result of the second part. So then we can go ahead and say self.feedForward, and here's where we'll invoke our second layer norm. So we can say self.second layer norm, and we're going to go ahead and pass in the first part. So this also does reflect the diagram that we talked about earlier. And this is actually exactly what we want to return. We just need to round it. So we can say that this is our result, like res, and then we just round it. So we can return torch.round of res and say decimals equals 4, and we're done. And we can see that the code works. We've finally written the transformer block, and in the next problem, we're going to code up the GPT class. So that's definitely going to be an interesting problem, so definitely check that one out next. Let's give a high-level explanation of transformer architecture, and specifically, we're going to focus on the decoder for this video, not the encoder, since that's what GPT uses. So why don't we just start with the embedding layers. So we're going to actually have two embedding layers. One of them is called the token embedding layer, and the other is called the positional embedding layer. So we'll discuss this one over here. And the goal of these embedding layers is actually to learn or train feature vectors. Specifically for the token embedding layer, the goal is to learn or train a feature vector for every single token in our vocabulary. So let's say we are doing a word level language model. So we can think of this embedding layer as actually a lookup table, and that lookup table will be of size vocab size, where vocab size is actually the number of different words that this model can recognize. So maybe the total number of unique words in our body of text that we're training the model on. Vocab size by embedding dim, where embedding dim is actually our choice. And the higher that we make embedding dim, the more complex of a relationship the model can learn. Next is the positional embedding. So this is also another lookup table, except this one is actually going to be context length by embedding dim. You may have heard of context length discussed in the context of large language models. You might know that ChatGPT has a context length of 128,000, specifically GPT-4. And context length is essentially how many tokens back. So when you're talking to these language models, how many tokens back in the sequence can the model read? Because at some point, it has to essentially cut off and say, okay, the model's not going to factor in anything that was this far back. But how far back can the model actually read? That is the context length. And similarly, during training, when we are feeding in batches and batches of training examples, we will actually be feeding in B by T tensors, where B is the batch size and T is the length of each, say, sentence in this training batch. And T will actually be the context length during training. So the positional embedding is essentially another lookup table that has context length rows in it. So this would be from 0 to context length -1 in terms of the rows or indices of that table. And the number of columns or the size of each row is also the embedding dimension, where we are essentially going to learn a vector of size of embedding dim for every single possible position. So what are we actually passing into the positional embedding layer? Because we know for the token embedding layer, we're literally just going to pass in the input tokens themselves, and the embedding layer here is actually going to then look up the feature vector for each token, because we have vocab size number of rows where each row corresponds to a token in our vocabulary. However, if the rows here are going from 0 to context length -1, then that's actually corresponding to positions or indices in a sequence. If we sent in write me a poem, we would say that write is at position 0, me is at position 1, a is at position 2, and so on. So to pass in, what are we going to pass into the forward method for the positional embedding layer? We're actually going to pass in the following, torch.arrange of capital T, where torch.arrange actually generates a tensor of size T that is sorted in order where its values go from 0 to capital T -1. And that's how we would essentially want to index our embedding lookup table. And once we have the token embeddings generated, once we have the positional embeddings generated, we simply go ahead and add them in. We just add those two tensors together before we'd feed them in to the transformer block. Next is the transformer block. Once we have actually added our two embeddings together, the token and position embeddings, we're going to go ahead and pass that in to the transformer block, this gray rectangular box over here. And this part actually does the heavy lifting within a transformer. This is what allows the model to predict the next token in the sequence so well. And the most important parts of the transformer block, we won't go super in depth about this entire box over here. I actually got a separate video on that, but we will kind of give a high level explanation for what it's doing and how to code it up. So the most important part is probably the masked multi-headed attention. And that might sound like a mouthful, but this is essentially the communication part of a transformer. Communication. We know that we pass in sequences of words into transformers. So let's say we passed in write me a poem. At some point, the model needs to actually realize which parts of this sequence of words to pay attention to, and specifically which pairs of tokens are more important. So in the attention layer, the model will actually consider every single pair of tokens, this pair, this pair, this pair, and actually every single pair of tokens in any sequence, and the model will figure out which pairs of tokens are actually relevant to each other. So we know that write and poem must be relevant to each other, because how else would the model actually know what to write? The model shouldn't write a book, the model shouldn't write a movie, rather the model needs to know that a poem needs to be written. So the model will actually let these tokens talk to each other, so to speak. The model will consider every single pair of tokens until the importance of every token pair relationship is determined, and then the model can focus on certain parts of the input and appropriately predict the next token in the sequence. The other most important part of the transformer block is the feed forward component. And the feed forward component is actually just a bunch of linear layers kind of stacked together, as well as nonlinearities like the ReLU function. And if attention is communication, we can actually say that the feed forward part, or vanilla neural network part, is computation. The model is going to learn a ton of weights and biases, similar to a linear regression, in order to encapsulate the entire relationship between all the words in the input so that the model can appropriately predict the next token. So that's the transformer block. It does the heavy lifting within the transformer. However, if you were coding up the GPT class, let's say we are coding up a class called GPT, you'll actually be given the transformer block class, and you can treat the transformer block class as a black box. However, when you actually are coding up the full transformer in the GPT class, you're going to actually notice this NX in the diagram. And that actually indicates that we're going to have many blocks in sequence. So what actually occurs in a transformer is the output of the transformer block. So the output over here is actually passed back in to the transformer block n number of times, where n is essentially the number of transformer blocks, and this is predetermined beforehand. Obviously, as we increase the number of blocks, the model gets more and more complex, and the model can learn a more and more complex relationship with more parameters. But to actually implement this into code, we're actually going to use something called nn.sequential. So in your GPT class, in the constructor, you will define something called nn.sequential. And you can actually treat this just like a Python list. You can call .append on an nn.sequential with the only restriction that the only thing this list can contain is other neural network layers. And then once you actually call the forward method of the nn.sequential object, once you call the forward method of this object, it will actually call the forward method of every single block that was passed in to this list in order from left to right. So that entire process of passing in the output of one transformer block all the way back in would be handled by that line of code, and you will find that incredibly useful if you're ever coding up the GPT class. One additional component that's actually not included in this original famous transformer architecture is that in GPTs, something that has been found to work really well is after the last transformer block. So right here, an additional layer norm is used. So that's an additional nn.layer norm. And we know roughly at a high level the benefits of a layer norm by actually making sure that our data is centered around the mean and has an appropriate standard deviation. We find that we don't have such crazy extreme range of values in our neural network, and the training process is actually much smoother. So we're actually going to have one additional layer norm before the linear layer and the softmax layer. And the linear layer is something that we can actually think of as a vocabulary projection layer, because the dimensions for that linear layer, it will actually have vocab size. It will have vocab size neurons in that layer. So out features for that linear layer would be vocab size. And that's because the model needs to figure out what the next token is, and it's going to output a bunch of probabilities, specifically vocab size number of probabilities, as we will have a probability for every single token in our vocabulary, as every single token in the vocabulary could technically come next. And of course, last, we will have the softmax layer. We will have a softmax layer over here, which will squash all our values to be between 0 and 1, so that we have a true probability distribution. Next, I would highly recommend jumping into the code and coding up the GPT class. Your job will be to write the constructor or init, as well as the forward method. And once this is done, you could actually train this GPT and then go ahead and use it for text generation. So I highly recommend jumping into the code. We're finally ready to code up the GPT class. And once we've written this class in the next problem, we'll actually get to see the model generate text. And this neural network that we're about to code up actually follows the architecture that almost all LLMs use, including ChatGPT, as well as many others. And we are going to be given a class called transformer block that's going to be in the starter code so that we don't have to actually code up this entire gray rectangular box that is repeated nx times in the diagram. And that class is actually then going to make use of other classes like multi-headed attention and the feed forward neural network class. So you might have previously coded up the transformer block in a different problem. Now we're actually going to use the transformer block to code up the entire architecture from start to finish. And this diagram is actually from Google's 2017 paper, Attention is All You Need. And this is one of the most influential papers in machine learning to date. And usually papers, I would say, are not super important to actually read, but if you're interested, definitely check that one out. And the forward method should return a batch size by context length by vocab size tensor. We can see that over here, and we'll explain why that's the appropriate shape of the return tensor in a second. And the output layer will have vocab size neurons. So that's specifically talking about this linear layer over here, the one in purple. And each neuron in that layer corresponds to the probability or likelihood of a particular token coming next. So just like in the handwritten digit problem, if you solve that one, we can actually have 10 output neurons corresponding to digits 0 through 9. And the number in that neuron, the number in that output neuron represents the probability that the passed-in image is that digit. So each neuron here is like the probability that the token corresponding to that neuron. So let's say we had V for vocab size total number of words or characters or tokens in our vocabulary. Then we can think of our neurons as being indexed from 0 to V minus 1. And then we have the probability that that particular token comes next. So let's take a look at the inputs. So the model's constructor takes in vocab size. This is just the number of different tokens the model recognizes. And as we get to our embedding table, once we get to that, we'll see that's actually the number of rows in our embedding table. Context length, this is just the number of tokens back the model can actually read. So when you're talking to a large language model, at some point in the conversation that you're having, it's not factoring in stuff that's like really far back into the conversation. So what's that cutoff point? How many words or tokens are we talking about? That's the context length. The model dim. So this is the same thing as the embedding dim or the attention dim. In previous problems, if you saw a separate number for embedding dim and attention dim, that was just to kind of help with understanding that those are different layers in the network. But in reality, when we have multi-headed attention, we actually just say that the embedding dim is equal to the overall attention dim, right? With the overall attention dim is just like your number of heads times each individual head size. So I definitely recommend reviewing multi-headed attention if you're a little rusty on that. And I can link something in the description, like a problem or a video for that. But we actually just refer to the embedding dim or the attention dim as the overall model dimensionality. And the larger this number is, the more complex the model is. And just for reference, GPT-2, so that was like before GPT-3, had a model dim of 512. And then obviously this got even bigger with GPT-3 and then GPT-4. Number of blocks. So how many instances of the transformer block class do we want to make? We know in the diagram that it is repeated nx times. So what is n? That's num blocks. And then num heads, we need to know how many heads of self-attention we're going to do if we're doing multi-headed self-attention. And then context. This is what the forward method takes in, right? In order to actually train the model, we need some sequence of text. We can actually see an example over here, or if we were, say, actually using the model for generation, before we generate text, the model needs to have something to start with. So that's what we store in context, and that's what the forward method of the GPT class takes in. Okay, let's explain the input example. So here we're actually just defining those constants that the constructor takes in. Those aren't super important to focus on. However, I do really want to explain this input and its shape and why this should make sense. So we know the input to the forward method is actually supposed to be B by T, because we train these neural networks in batches. So we'll have many sequences passed in parallel. And that is how many we're passing in parallel is the batch size, capital B. And that is just one here. There's only one sentence or one sequence. But based on like the shape of this 2D list or 2D tensor, we can tell that there is still an additional batch dimension going on there. And then T, so during training, T is actually just the context length. So we can see that there were 5 tokens passed in. With great power comes great. And then the model is supposed to make predictions for the next token, given all the training examples within this sequence of tokens. So given the context of with, the model will predict what comes next. Given the context of with great, the model will predict what comes next, and so on, all the way until the model has the entire input. With great power comes great, and then the model predicts what comes next. And we see that the context length is 5, right? And this kind of makes sense that why would we actually have necessarily a capital T, basically how long the sequence is greater than 5, because the model can't factor in. Context length is the greatest amount of tokens the model can even factor in to its next token prediction, right? So with great power comes great. That's already 5 tokens in a row. The model wouldn't even really be able to factor anything else more than 5 tokens in. It would have to start. If we added like another token here, the model would then have to not factor in the first token to actually predict, what comes next. So that's just an example of context length during training. So let's take a look at this dictionary now. So we're going to assume that the model is consistently using this internal mapping. So we know models don't actually take in strings, right? Each of these tokens needs to be converted to an integer. That's how we actually feed in strings into models for natural language processing. And this model's mapping, any model's mapping is pretty arbitrary. As long as it's consistent, that's all that matters. So we can say with maps to 0, great maps to 1, power maps to 2, and so on. So in the final layer of the neural network, where we have vocab size or capital V neurons, we'll say that the 0th neuron is essentially corresponding to with, the first neuron is corresponding to great, and so on, all the way until the V minus 1th neuron. Okay, so the returned output, first let's explain the shape of it, B by T by V. So we know that batch size was 1, as we saw in the input. So it makes sense that this whole 2D tensor, or this whole 2D array over here, is actually wrapped in another one. We can see that there's another pair of brackets over here. So the batch size equals 1 is still maintained. However, for that example, for the first element in the batch dimension, or for every element in the batch dimension, we get a capital T by V tensor. And that's because for every single time step, for every single context or training example, the model is generating a vector of size capital V. And the reason we have a vector of size capital V is because that is essentially a list of probabilities, a probability for every possible token that could come next. So we'll actually see that the first row in this output tensor is actually the model's probability output. It's a vector of size V. We can see that there's V columns here, right? V equals 5. There's 5 unique words. With great power comes responsibility. Those are our 5 tokens. We can see that this dictionary has 5 keys in it. So we can see that our vocab size is clearly 5. Those are only 5 tokens that we're going to say this dummy example, this dummy model is dealing with. So back to the first row. The first row in this output tensor is the model's prediction, which is a vector of size V for the first context. And the first context is just looking at width. And then the second row, which is actually over here, it's 0 and then 0, and then we can see a 0.1 over here. The second row is the model's prediction, another vector of size V, for the second training example in context. So the second training example is with great, and then the model is trying to predict what comes next. We know power comes next, but the model doesn't actually get to see that. And again, the reason the model doesn't get to see that, it doesn't get to see the future tokens, the actual answer for each training example, is because in the self-attention implementation, and again, I highly recommend reviewing self-attention, multi-headed attention, if you're a little rusty on that. But the reason the model doesn't get to see those future tokens is because in the code, we actually apply a mask. If you look at the multi-headed or actually single-headed attention class, and then the multi-headed attention class makes use of the single-headed attention class. But in the single-head attention class, we apply a mask and we mask out those future tokens so that the model can't look at the answer for what it's actually trying to predict. So let's actually think about why this output would make sense. And let's say the model has actually been trained. So by this point, it's pretty good at actually predicting the next token. It's not just like an initial neural network and it's before training is done, where its weights and parameters are just completely random. Let's assume the model's been trained. So for the first example, we know that the only token the model is looking at is width. So the model will hopefully in a trained state be pretty good at predicting that the word great would come next. And we know great corresponds to the 1th index, and we can actually see that over here. The model is saying that there's an 80% chance that great comes next, if you just are looking at the word with, and there seems to be a 10% chance that the word power comes next. Let's see if that makes sense. With power. So that could be like the start of a logical sentence. So that seems reasonable for the model to still say that there's some chance for that to happen. And then the final column corresponds to responsibility. The 4th column is using 0 indexing. And there's a 10% chance that responsibility comes next. So that would be like with responsibility. And that seems reasonable too. But thankfully, the model is still saying that we have an 80% chance. We have an 80% chance that great, essentially token number 1, the 1th column, we can actually see that there's an 80% chance that great comes next, given the context of with. Let's take a look at the V size vector for the second row. So the second training example is the context with great. And hopefully the model does a pretty good job of predicting that power comes next. So we say there's a 90% chance for the 3rd column and a 10% chance for the last column. So the 3rd column here is corresponding to, 0, 1, 2, using 0 indexing, right? And that corresponds to power. So you can see that the model is saying that with a context of with great, there's a 90% chance that power comes next. The final column, so that corresponds to token ID number 4, is responsibility. So does that make sense? With great responsibility. Yeah, that could be reasonable. That seems like a logical sentence in English. So their model is still saying there's a 10% chance. We can see there's a 10% chance that responsibility comes next, but the model is still fairly confident, after training has been done. Let's say this sentence was actually in its training body of text. The model is fairly confident that power comes next with the context of with great. So that's good that the model is predicting that. I definitely recommend making sense of this row and this row, but why don't we skip to the last row and see if the model's prediction makes sense there as well. So we have this vector of size v, capital V equals 5, and this must be the model's prediction given the entire context. So with great power comes great, and the model is predicting what comes next. So we can see here that there's a 90% chance corresponding to the fifth column, so that's with 0 indexing corresponding to token ID equals 4, and that's responsibility. The model is saying there's a 90% chance that responsibility comes next, so we can see that this B by T by V shape does make sense. Okay, so now let's run through the transform architecture so we can see how we would actually code this up. So the first layer is this pink looking rectangle that is the embedding layer. And I actually crossed out the word output from this layer because this original transformer diagram created by Google was actually used for translation. They were working on models that can translate between different languages, and when we use the transformer for generating text, the architecture is slightly different. You've noticed that maybe if you've seen the original version of this diagram, we cut off what was on the left. That's because large language models like ChatGPT don't use that at all. And I explain that in more detail in my encoder decoder course. So this first layer of the neural network, this pink embedding layer over here, is actually how the model learns the meanings of the different tokens or words. We know that we have some sort of mapping where we map every single token to an integer, and the model then receives this list for a given sentence where each token is represented as an integer. However, those are completely arbitrary, and we need the model to learn some sort of deeper representation that encapsulates the meaning of each word. Ideally, the model would learn a vector that represents the meaning of each word, and we call those embedding vectors, and they're actually trainable and learnable through gradient descent. So we can imagine it being a lookup table. A lookup table, we were given a given token, we would actually look up the corresponding row for that token, and all the columns that are associated with that given row would actually just be the embedding vector or feature vector that is learned for that word. So the number of rows in this table should just be the vocabulary size, capital V. And this is because for that many tokens, that's how many tokens we want to learn the feature vector for. And the number of columns in this lookup table should just be the model dimensionality, since we know that is our dimensionality of our embeddings, and that's how many features we would essentially have to learn the meaning of each word. So then in the constructor for the GPT class, the way we would actually instantiate this embedding layer is by using nn.embedding. And we only have to pass in two things to nn.embedding. The first thing is the number of rows of the table, and the second thing is the number of columns of the table. Next, let's talk about the other embedding layer, which generates our positional encodings. So when we have a sentence in English, it might be one that we pass into ChatGPT. Let's say it's a command like write me a poem. This might sound kind of obvious, but it is something that we should clarify. When it comes to teaching computers to understand speech, the order of the tokens is actually really important. The positions of each token in this sentence. This token's at the 0th index, this token's at the 1th index, and so on. If we have something like poem, me write a, if we jumble the order, the meaning is completely lost. So we need the model to actually learn embeddings for each token's position as well, which means we're going to have another lookup table where the number of rows is just capital T, or the context length, so the model can learn a feature vector, again of size model dim, for each token position all the way from 0 to capital T minus 1. So then when we actually call this layer in the forward method, what are we passing in to the forward method of our positional embedding layer? Because this is going to be a separate nn.embedding instance than this one over here. What we would actually pass in is simply a vector of size capital T that simply has all the numbers from 0 to capital T minus 1, since that would essentially pluck out the rows of the table for each position in our sequential input string. And the way you can actually generate that tensor is using torch.arrange. It's going to arrange numbers from 0 to whatever the input is to this function minus 1. So you would just put in torch.arrange of t, and this is the tensor that you would want to pass in the forward method of the GPT class when you're calling the positional embedding layer. And of course, maybe I didn't clarify this before, but just to make it super clear, you would actually just be passing in the raw input, our b by t input. That's what you would pass into the actual token embedding layer. Then in the forward method, what we're going to do is we're just going to add the positional and token embeddings together, and then we're going to pass those in to a series of transformer blocks. So let's just go ahead and treat the transformer block as a black box for now, as we actually have an entirely separate coding problem explaining the inner workings of this box, masked multi-headed attention, the add-in norm, the feed forward, all the components within the transformer block. And this class is given to us, so we just need to know how to instantiate it in the constructor for GPT class, and then how to actually call it in our forward method that we're going to write. So since we're going to be instantiating a bunch of these, a bunch of transformer blocks based on the num blocks parameter that was given to us, we're actually going to make use of something called nn.sequential. nn.sequential. So you can instantiate this in the constructor for the GPT class, and then you can actually treat this like a normal Python list. You can call the .append method with the only restriction that anything you pass in needs to be a neural network class. It needs to be something that also subclasses nn.module. So each time that you append to this list, maybe you would loop over in the range of num blocks. You're going to append an instance of the transformer block, and every time you instantiate the transformer block, the only things that you'll see you have to pass in are the model dimensionality, as well as the number of heads. This is an input that's given to us, and the number of heads is simply the number of heads of self-attention. So you would define blocks, your nn.sequential, in the constructor for the GPT class. And then just to be super clear, the way you would actually do this in the forward method for the GPT class is you would pass in your total embeddings. This is just your positional embeddings plus your token embeddings. You're going to go ahead and pass that in to essentially the default calling method, which is essentially the forward method for the blocks. And the way nn.sequential works is for this list of modules that you've passed in, it's just going to call them in order. So it will pass in total embeddings into whatever's at the 0th index in this list, and then it will go ahead and pass the output of that into the next layer, the next transformer block. So the input comes all the way back in as many times as we have elements in this nn.sequential. So you'll simply get the output like this. You will pass in total embeddings into blocks, and then this is the output of the transformer blocks. Okay, so what's left? The bulk of the code is done. Even though the transformer architecture that was originally developed, this diagram does not include an additional layer norm over here after the transformer block and before this linear layer, it is customary to include one additional layer norm, so an additional instance of nn.layerNorm defined in our constructor that we then call in the forward method. Researchers have found that these large language models get way better results if you do an additional normalization, an additional layer norm before the final linear layer. And again, for a refreshment on what layer norm does, I highly recommend checking out the transformer block video where I explain every single inner working inside the transformer block. So the final linear layer is over here, and this is what is going to get us the output to be in the shape we want so that we can actually extract predictions for the next token. We know that the input to it is b by t by d, where d is the model dimensionality. And we know that we want to get something that's b by t by v, where v is the vocabulary size. So the way we'll do that is by appending a linear layer, having a linear layer defined in the constructor of the GPT class. And in features for this linear layer will be a model dim, as that is capital D, and then we will pass in V or vocab size for out features. And this will actually get us the prediction in the shape that we want, and this does make sense given that example we talked about at the start. And lastly, for the softmax layer, again, the whole point of the softmax layer is so that we actually get numbers between 0 and 1, because we want those tokens, those final predictions in the b by t by v tensor, we want those numbers to be between 0 and 1, so we can think of them as probabilities. So you can actually instantiate a softmax layer in the constructor of the GPT class. That would be like nn.softmax, and you would pass in the dimension along which you want to normalize or make everything add up to 1. Well, that would just be the final dimension, right? The vector of size capital V is our list of probabilities. So you could just pass in dim equals 2, 0, 1, 2, or you could say dim equals -1 for the final dimension. And then you would simply call the forward layer of your softmax instance in the forward layer of the GPT class. Or since the softmax layer is sometimes thought of as simply a function rather than a layer, you can actually just call nn.functional, and then kind of like nn.function.softmax in the forward method for your GPT class, and you don't have to worry about instantiating anything in the constructor. And then this function would take in two things. It would take in your tensor as the first input, what you actually want to perform softmax on, as well as the dimension over here, which we would just pass in -1 for. And that's it. We're finally done explaining this entire transformer architecture that we've been building up to across all these videos and trying to understand how this neural network works. Before we jump into the code, I just wanted to say thank you for making it this far into the videos, and then two other things. One is that we're actually not done. We still, even after this coding problem, have one more, and that's going to be where we finally generate text from the model. We see this neural network architecture in action and working like a GPT. So we're finally going to be able to generate text from the model. The next problem, you're actually going to write the generate function, which is a bit different than the forward function for this class. And we'll actually get to return a string, and that's how like the test cases will work. Like we'll see if the string that your GPT returns back to you based on some sort of prompt actually matches what the string is supposed to be. So that's going to be a pretty cool problem to test to see if you can write the generation code, the logic that actually makes these transformers generate code. And the next thing I wanted to say is that I highly recommend, if you need to, reviewing any of the previous like videos or problems in the series, all the way from, I think the first problem we started with was like gradient descent, and then we worked all the way through like linear regression, sentiment analysis, multi-headed attention. And these problems and these videos will always be free. And if you need to review any of these concepts at any time, I highly recommend that. Okay, let's finally jump into the code for the GPT class. And I recommend reviewing like the other classes that are provided below just to refresh yourself on those concepts. But for the most part, we'll just treat the transformer block class like a black box. So the first layer in the neural network is the word embedding or token embedding layer. So that'll be something like self.token embedding equals nn.embedding, and the number of rows, we know that's the vocab size, and the number of columns, or the size of that vector, is the model dimensionality. Then we're going to have our positional embeddings layer. So positional embeddings is nn.embedding, and the number of rows here is actually just the context length. We're going to go all the way up from 0 to t minus 1, and then the size of each vector, or the number of columns, is also the model dimensionality. Then we need our transformer blocks, right? So we can say something like self.blocks equals nn.sequential, and then something like for I in range of num blocks, we know we actually want to append to this. So self.blocks.append, and then we're actually going to do something like transformer block. We're going to use that class that's below. And then we can go ahead and just pass in the two things that it takes. And it takes in the model dimensionality. If you check the constructor, that's way below. It takes in the model dimensionality and the number of heads. And then we're actually going to need our final layer norm, which actually comes before the final linear layer. So we can say something like self.final layer norm equals nn.layer norm. And then if you've solved the transformer block problem before, you know that the layer norm class or the layer norm constructor just needs to take in the dimension along which to normalize. So this thing is going to take in something that's actually b by t by d, and it's going to actually return something that's still b by t by d, but it normalizes along that model dimensionality, that third dimension. So we just pass in model dim. And then we're going to want to do our final linear layer. So self, we can often call this the vocab projection, because we're projecting down to the vocabulary size dimension. So the vocab projection is nn.linear, the input features is model dim, the output features is vocab size, and that's actually it for our GPT constructor. One small thing though, since transformer block is an inner class, we do need to refer to it as self in Python, and for the softmax, we'll just use the function and do that in the forward method below. Okay, so now let's pass in our input, also called context, all the way through the transformer architecture. The first thing we need is our embeddings. So we can say something like token embeddings, or we can just say token embeds equals self.token embeddings, and we pass in our context. So this is going to be something that is b by t by d. Since for every token, we get that vector of size d. Then we need our positional embeddings. So we know we're going to call the positional embeddings function, or the positional embeddings layer. And what do we want to pass in? We want to pass in torch.arrange of t. But how do we actually get t? Well, we can actually get that from any of these tensors. So we can say something like b by t by d equals token embeds dot shape, and that will unpack this dot shape tuple. And then we can simply pass in t over here. So then we know that our total embeddings, or our sum of embeddings, is token embeds plus positional embeds. And this is what we then want to pass in through the blocks. So we can actually say self.blocks pass in total embeddings, and that will then be passed through all n of our transformer blocks. Then we know this goes through the final layer norm. So self.final layer norm, we pass in this into there. And then the output of the layer norm goes into the vocab projection, the linear layer. So self.vocab projection takes in that output. And then this is almost the final output. So we can say this is like the unnormalized, right? It's not between 0 and 1 yet. We have to apply softmax for that. So nn.functional.softmax, and we pass in the unnormalized, pass in dim equals -1, as we talked about earlier. And this will actually be our normalized probabilities. They're between 0 and 1, so I'll just call it probs, and it's been normalized now. And then this is what we want to return. We just need to make sure to round our answer to 4 decimal places, just so the test cases are consistent. So we can say return torch.round of probs, and then decimals equals 4, and we're done. And we can see that it works. We've finally written a working GPT class. There are so many concepts embedded within this, so definitely leave a comment if there's anything you would like me to go more in depth on, and I'll just make a video on that. If you're curious as to how I wrote the test case for this problem and to how it's actually checking the correctness of your code, I simply created a random context and then randomly initialized the weights of your model, which is actually automatically done by PyTorch, and then I'm checking to see if the probabilities, the output tensor returned by your forward method, is actually matching the correct solution code's output tensor to 4 decimal places. And by the use of all these seeds, I'm able to ensure that everything is reproducible and there's actually no randomness and inconsistencies in the inputs and outputs. Next, I would highly recommend jumping into the Make GPT Talk Back problem. In that problem, you'll implement the logic to make GPT generate text, and it's going to be a really nice, satisfying ending to this sequence of problems. So how do we actually generate text from language models? Let's say we're going to treat these language models, these transformers like GPTs, as a black box. How do they actually generate text though? So after we watch this video, there will be a coding exercise to generate new Drake lyrics using a trained model. And I highly recommend doing that exercise and then playing around with the model. So how do we actually generate the lyrics? So first, let's treat the model as a black box. So this is our model. It's some sort of trained GPT. And we'll explain what it takes in and what it outputs. So it actually takes in a tensor of size b by t. B is something called the batch size, and it represents how many independent examples or requests in parallel we're processing. For generating text, let's just say batch size equals 1. So we'll say B equals 1. The T is actually really important though. The T is actually equal to the length of the input sequence. So if we're using word level tokenization and we said something like write me a poem, that would actually be a capital T of 4. And what the model outputs is actually something of size B by T by V, where V is the vocabulary size. So it's the number of unique words or tokens that this model recognizes. And this should make sense because for every single time step, we have this vector of size V. So for every single time step, for every single space or every single position in some sort of input sequence, maybe that input sequence is 4 words, like write me a poem, we're getting a vector of size V, and that vector of size V is actually a list of probabilities. And if it's of size V, then we can actually think of index 0 in that vector as corresponding to the probability that the token associated with index 0 comes next. And the same for index 1, index 2, and so on, all the way to index vocab size -1. So in short, we have vocab size or capital V entries for every time step, where every entry in that vector corresponds to the probability that the corresponding token comes next. So after we've passed in our input, something like write me a poem, so that's B equals 1 and T equals 4, we get something that's B by T by V. So let's actually go ahead and explain how the next token is chosen in more detail later in the video. But given that list of probabilities, there's going to be some sort of sampling algorithm. You can think of this as reaching into a bag of marbles, and the marbles that occur more often are more likely to actually get picked out. It's essentially going to be the same concept here. We have a bunch of probabilities of which token could come next, and using those probabilities, we're actually going to pick one token to come next in the sequence. So let's say the input was write me a poem. Let's say we had a bunch of probabilities that came out of the model, and the token that we actually ended up choosing to come next is stanza. Well, what we go ahead and do to actually generate text continuously from the model is we go ahead and append or concatenate this word to the previous input. So now the input says, write me a poem stanza. And then this is actually going to go ahead and be passed into the model. So we have write me a poem stanza, and this is going to be passed into the model. We're going to call the model again, and we get another output. And this time, after we choose from the probabilities, let's say we get the token 1. So then we would actually append that over here, and then we would get stanza 1. And then we would actually go ahead and pass write me a poem stanza 1 into the model again, and the model will actually output another probability distribution. And this process of continuously calling the model over and over again in some sort of cyclic manner is actually how we keep getting the next token in the sequence and how we can generate long text. And just to make sure this is super clear, after we pass in write me a poem stanza 1 into the model, the next token that comes out should hopefully be either the colon operator so that we can actually start the poem, or actually the first token in the poem. And then we would keep calling this model repeatedly to generate the entire poem. So how is this actually going to work in our coding exercise? Instead of passing in an instruction, all we're going to pass in is a start token. It's essentially a dummy token that tells the model to start generating text. And this is actually how text is generated from language models when they're in their pre-trained state before we've actually fine-tune them on a Q&A data set so we can talk back and forth with the model. However, they can still generate text very well. So our start token or initial context is just going to be 0 in a tensor, and that will be given. But after calling the model once, it's going to output something that is 1 by vocab size, assuming a batch size of 1 and t equals 1. However, after calling the model twice, right? Because after calling the model once, we're actually going to append or concatenate the model's output to that initial starting context, that starting token. And after calling the model twice, the output is going to be b by 2 by v. And of course, after calling the model 3 times, the output is going to be b by 3 by v. So we actually only care about the final time step, right? The next token that's going to be predicted in the sequence based on everything that's come so far, all the previous tokens. So whenever we actually extract the output from the model, the output of the models forward, we always are going to need to focus on the last time step. And this is how we can index the output to do so. So once we get our probabilities, such as by applying softmax to the model's output and having numbers between 0 and 1, once we have a list of probabilities, we need to actually choose a token. We need to do something called choose the next token, because we don't actually know which token is going to come next. All we have is a bunch of probabilities. One option is just to pick the token with the highest probability, but this actually leads to really boring results, and the models don't actually give human-like context or human-like text generation. So we actually are going to have to call a function in PyTorch called torch.multinomial, which is going to simulate the process of sampling. So the process of sampling can actually be likened to choosing marbles from a bag. The marbles that occur more often, the colors that occur more often, are going to be the ones that you get most of the time. But every once in a while, you will get a marble that occurs less often because there's still a chance that that marble could get chosen. The same kind of holds for the output of the model, which is of size v or of size vocab size. The tokens that have higher probabilities are the ones that are more likely to get chosen, but we still want the less likely tokens to get chosen sometimes instead of only choosing the max, instead of just calling torch.max or something like that. So once we have our probabilities, we're going to call torch.multinomial, and torch.multinomial is going to sample or pick a token for us. Then, once we have the returned tensor from torch.multinomial, which will essentially be a tensor with just one element in it, the next character or the next token in our sequence, we're actually going to append that to our context. We're going to append that to our growing context. We're going to concatenate it with our growing context. And at the next iteration or the next iteration of the loop, we're going to call the model again, call the forward method for the model again. However, there is one limitation that we still need to take into account, and it is actually something called the context length. The context length of these models, these language models. You might have heard that GPT-4 has a context length of 128K, and the context length actually represents how many tokens back into the past, of the sequence can the model read? Because this actually has to be cut off somewhere as we don't have infinite compute. So obviously higher numbers for the context length are going to yield better results, but the context length does have to be established somewhere. So in our iteration or in our loop for kind of generating new text where we keep continuously calling the model prediction or calling forward for the model, we know that this context is going to be growing. We saw earlier that we had write me a poem, and then write me a poem stanza, and then write me a poem stanza 1. But as this context gets too long, if this context ever exceeds context length, just in the implementation, it is an important detail that we are going to have to truncate the tokens at the start so that we're only looking at the previous context length number of tokens. So next, I would highly recommend jumping into the code. You will actually get to run your code against test cases and see if the string that you return is correct, the string that represents GPT's prediction. And then you will have a working model that can generate new Drake lyrics. And of course, you could just switch the dataset to a different text file if you wanted to generate, some other sort of text. So I'd highly recommend jumping into the code, and then you can check out the Colab linked on the problem, which will actually allow you to play around and generate new lyrics. And let's test our code and let's see if it works. So we can go ahead and run this cell. And these actually look like real lyrics. In fact, we can run it again. We can see if we get real lyrics as well. And yeah, we get some different lyrics. And of course, we can increase the number of characters here and get even more lyrics. Okay, this is our final problem in this list of problems, and we're finally going to generate text. We're finally going to generate text using all the code we've written so far. This problem is going to combine concepts from this entire series, and we're finally going to use the GPT class that you wrote. We're going to use that exact class. One of the inputs is actually an instance of that class, and we're going to use it to generate text. I took the model that you coded up in the previous problems, the GPT class. I made an instance of that class, and I trained it on a raw data set of all of Drake's songs. So what's being passed into you is actually a model that is specializing in generating Drake songs, since that is the body of text that it learned to model really well during training. And we're finally going to get to write the code that actually generates text from models, these large language models. So it turns out that implementing inference, this idea of using a trained model and actually using its weights to generate new things, is called inference. And it's a bit more complicated than just calling this forward method from the GPT class over and over again. And this is a valuable skill to really understand, because then you could actually download open source models. You could download open source weights from online and implement inference for them on your own, and you actually generate text. And that can be a really fun side project. So, and the reason it's more complicated than just calling forward in a loop is because forward is not outputting like a clear-cut output of what the next token in the sequence should be, right? If we pass in my name is into this model, let's treat the model as a black box. This is our model. And if we actually pass in this sequence, and let's say we know the answer is Bob, and let's say the model has been trained really well, and the model knows that the next word is Bob, but it's not going to give us a clear-cut answer like this, right? That's not what this model outputs. This model outputs a vector of size, vocabulary size, or capital V, where that's the number of tokens that the model was trained on. We have a bunch of numbers, each between 0 and 1, and if we go to the index where Bob is, that's actually going to be like a really high number, maybe like 0.95. So the model is outputting a bunch of probabilities of each possible next token, whether that's a character. In this model, it's actually going to be a character, but it can obviously be a word. It's just some token. So given a bunch of probabilities, how do you actually choose the next token? Because it turns out just taking the highest probability token doesn't necessarily yield the greatest results, and we'll explain why in a bit. The model is only also allowed to read context length, number of tokens back into the past, right? As we're generating text, these generations can keep growing and growing and growing. And we're going to need to actually truncate off tokens that are farther back than this threshold at every iteration. And the way that your code will actually be validated is we'll just check to see if the string that GPT is returning back to you, whatever text, actually matches what it should be. So let's try and understand this example. We're given an instance of the GPT class, and that's going to be the model variable. Then we're told how many new characters to generate, and we're given the starting context. So if the model is a black box, this is our model. We go ahead and pass in some sequence of tokens of length capital T. We're going to start off here by just passing in one token, and specifically is 0. And so since we just have one token, we can say that capital T equals 1. And if you look at the vocabulary dictionary, remember, we actually encode our tokens as numbers, right? When we're doing NLP, we can see that 0 is corresponding to the new line token. This is corresponding to the new line token. And that's going to kind of be our start token. That's going to kind of be like a start token to tell the model, hey, start generating text. And in this case, since we train the model on lyrics, you can maybe think of the new line token as say, okay, start generating a new stanza or a new verse or something like that, right? And we actually are going to then get a probability distribution. We're going to pick a token. So we're going to choose the next token, And then once we decide that, we're actually going to concatenate it to our original input. So now this will be of length T plus 1. That'll be the size of the input. And then we'll call the model again inside some sort of loop. We'll get the next token, and then this process just continues. So we need to be told how many times to actually generate new characters, and that's this input over here. And of course, as this input grows, right, as we are generating new tokens, appending them back on to the context variable, as we are appending to context and the context is growing, at some point, those tokens from the past, maybe those starting tokens need to be cut off if the input is getting too long for the model to actually process. So that's our context length. And then again, this is just a dictionary for encoding integers to characters. This is going to be a character level model instead of a word level model, but all the concepts are exactly the same. And although your output, when you actually run the code, when you solve this problem, it's not going to match exactly this just due to computational limits within the browser. I went ahead and ran this model. So I used the solution code for this problem and used your GPT class that you wrote in the previous problems. And this is the output I got for only 60 characters. So you can count this. This is 60 characters. And we can see that it's something that actually resembles like Drake lyrics. So that's pretty cool. So now let's jump into how it works. So this is going to be our general workflow for this generation loop. From the model output at every iteration, we're obviously going to call the forward method of the given model at every iteration using our growing context, which again, we have to remember to truncate if it gets too long. We are going to then get probabilities. However, the output of this model, as the starter code says, has actually been before softmax is applied. So they're not actually between 0 and 1 yet, and we need to actually get those probabilities. So we're going to actually use nn.functional.softmax. And of course, we're going to use the last dimension. So we say something like dim equals -1, so we can make each row actually sum to 1. However, the model's output, before we even apply softmax, the model's output is of shape B by T by V, right? For every single token, at every single time step, we have this vector of size V, all the probabilities. But we've actually been calling this model over and over again inside the loop, and this T has been growing. It starts off with T equals 1, and then T equals 2, and then T equals 3 as we generate the tokens. But each time, we only really care about the next token, right? The next token that's going to come in our sequence. So we only actually care about the last time step here. We don't care about the model's predictions for the previous time steps because we already have the answers, or we've already chosen a token. We've already chosen a token from the probabilities and done our whole sampling thing, which we're about to explain. We've already chosen those tokens. So we just want to actually index the model output at the final time step. So we might do something like, let's say we had the model prediction stored in some kind of variable, the model output. You would actually want to leave batch size the same, but take the last time step. And of course, you want to grab all the vocabulary entries, all the probabilities. So you would leave the vocabulary dimension the same. Then you can apply softmax. And from those probabilities, we're going to do sampling. So let's talk about sampling. So given a bunch of probabilities, one choice is just to keep choosing the highest probability token. Look at the max, look at the index of the max probability, and simply choose that token. However, we're instead going to do something called sampling. Sampling can kind of be likened to drawing marbles from a bag. Let's say there's a bunch of marbles of different colors, and some colors appear more often than others. The ones that appear most often, if you keep repeatedly drawing into the bag, those are going to pop out more often, but occasionally you can still get the lower probability, the lower count marbles. That's exactly what we're going to do here, and there's a function called torch.multinomial that is going to simulate this sampling process. All we have to do is pass in the probabilities, right? So that's after we applied softmax. The number of new essentially drawings that we want to do from this bag of probabilities, that's just one. And then for reproducibility, so that your test case is not random every time your test case is output, you need to pass in the generator. Why do we sample? Why are we doing sampling instead of just taking the max probability token? I go into this in more detail in the background video for this problem, but the short answer is if we let the model occasionally choose like the second most likely or the third most likely, we can get a lot more diverse and interesting outputs because it's not like the model is forced to just take one path. Instead, there's different paths that the generation can go down, right? Because we know that at a given iteration, if we choose a given character like A, right, instead of a character like B, then that is going to affect the future tokens that are generated because they're all conditioned. They're all kind of dependent on the previous tokens that came before it, right? So we can get some more interesting and some more fun outputs if we occasionally choose maybe the slightly less likely token at a given iteration, because then this can allow the model to go down a different path and generate something different. Okay, we're finally ready to jump into the code. Since we're going to be returning a string that's actually going to be growing at every iteration, depending on which characters we generate, first I'm going to declare a variable called result, which is just going to hold the list of generated characters, and then we can just convert this into a string at the end. And again, to maintain the reproducibility here, we actually have to have this generator, which is going to keep track of all the random numbers and make sure that everything's consistent. So you actually have to set the generator to the initial state at every iteration to make sure everything's consistent. If that doesn't make a ton of sense, don't worry, it's not too important. The only thing we really need to do is just have our code here. And we've said that it's going to be some arbitrary number of lines. And then you're going to call torch.multinomial on this line over here, right? Because we know that there's going to be a call to that sampling function at some point. And like we said earlier, we're going to pass in the generator. And then right after that line, we need to set the state again and then finish our code, however many lines that is for the loop, for the body of the loop, and then it starts over again. So the first thing we're going to go ahead and do is check to see if we even need to do any truncation. So has the context grown long enough to where it's longer than context length? And the way that I'm going to do this is since context is b by t, right? So we know context is b by t, and I'm actually going to go ahead and check the length by using the second dimension, right? So an easy way to check the second dimension is just take the length of the transpose version, because len always returns the first dimension, right? If it's b by t, the len of context is b, right? But if you actually transpose it, you flip it into a t by b, you could say len of context dot t. So dot t for transpose actually is that t, not to be confusing between those t's. So then if we say, okay, if the length of context dot t, so transpose, is actually greater than the context length, then it's too long and we need to truncate. So we could say context equals context, preserve all the batch dimensions, and we can go ahead and say from context length. So go context length tokens backwards. And then so that's kind of what negative context length means, right? Going context length tokens backwards from the end and then colon all the way to the end. So then we'll preserve everything from that point onwards. Then based on this context, we need to get the model prediction. So we can say prediction equals model.forward, or again, just use the default calling. So we can pass in context. And this is the truncated context that we passed in. Then we want to focus on the last time step. So you might say last time step, because again, we only care about getting the next token. So prediction, and then we might say colon, -1, colon, as we talked about previously. So instead of this being b by t by v, right, this one is b by t by v, this one is just B by V, which is actually what we wanted. Then we can get our probabilities by calling softmax, so nn.functional.softmax, pass in that last time step, and we want to normalize along the vocabulary dimension, make every row in this tensor actually sum to 1, and all the entries need to be between 0 and 1. So pass in dim equals -1, and now we can actually call torch.multinomial, right? So we can actually go over here. It says now that we have our probabilities, we can call torch.multinomial. So let's go ahead and do that now. We can say next char or next character is torch.multinomial, and we know we need to pass in the probabilities. We know we need to pass in the number of new, essentially how many times do we want to draw out of this bag. So that's called num samples. So you can say num samples equals 1, or you can just directly pass in 1. And then we do have to pass in the generator just to make sure the sampling is consistent. And then, we want to set the state just so everything's consistent, but we don't have to touch that at all. And here's where we're going to finish out the loop. We know we need to grow the context and actually append the new character we just got. So we can use torch.cat for that, concatenation. So torch.cat, we pass in our tuple that torch.cat expects, and we just want to concatenate context with the new character. So then we can actually say dim equals -1 over here. So that takes it from something that's B by T, that's the initial shape of context, to something that's B by T plus 1. That's what passing in dim equals -1 does over there. We're focusing on this dimension over here. And then we can actually append to res, right? So we can actually say int to char, that's that dictionary that we had earlier, right? We want to index this with whatever token we chose. So we can say next char, and next char is supposed to be like an integer, right? Because the model is thinking in terms of these token IDs, not the literal strings themselves. The model is thinking in terms of the integers that represent each string. However, this is actually going to be a tensor still, since it's actually something that's returned by torch.multinomial. So we can simply do .item, and .item extracts the number out of a tensor of size 1. So if you had a tensor, which is like wrapping around some sort of single constant, and then if you call .item, it gives you like the actual number, the actual scalar. So that would give us 5 over there. And then this is just what we want to append to res. So we can say res.append of whatever that dictionary gave us, whatever character that was. And now we're ready to actually return the string. However, we need to return a string, not a list. So why don't we just join all the entries in the list with essentially the empty string. So we can say return empty string dot join of res, and this is going to join all the elements in the list with the empty string. And we can see that the code works. Next, I highly recommend checking out the linked Google Colab notebook in the description. You don't have to write any more code. In fact, you're going to see your code, this exact generate function that you wrote here, being used in that notebook. And all you have to do is click run on each cell one by one, and you'll actually, every time you run it, you're going to get new Drake lyrics. So that'll be really interesting. She know what she need, she blessed, giving my best, got my heart on my sleeve. Since you've made it to the end of the video, I have 2 more resources for you. The first is our accelerator. We've helped countless people land their dream offer in AI engineering. Head to the link in the description to learn more. The second is another YouTube video. In that video, I break down the invisible hiring funnel and how you can take advantage of it to land job offers on autopilot. Check it out, you don't want to miss it, and I'll see you soon.